one somewhere.
This meeting is being recorded.
Yes, it is. Thank you. Let's see. Well, it doesn't show up immediately. Let's see.
Shows up on our side.
Actually, I'm named after the first California president of the universities.
Oh,
his name was
cool.
Robert G. Sproul.
Very
So it
cool.
was spelled with a U.
Okay, well, it's close.
Sproul Hall at Berkeley.
It says we have an unstable network again. But we've got more bars than we had yesterday.
I'll be right back here in a moment. I got to reset my headphones. These are dying.
Don't you hate when that happens?
Thank you.
And it's 8:30, so we're going to start, and I assume people are going to be trickling in. So, good morning.
Good morning.
Morning.
Good morning. I'm going to do the best I can with what voice I have. And one thing I want to do is
speed was it?
I was asked yesterday. I was asked to just go back and.
No, that's frequency. F is frequency.
There we go. Okay, I just muted you. Talk away. Okay, so this basic formula, C is equal to F lambda, is C is the speed of light in free space. And somebody had asked lambda, Lambda, Greek letter lambda. And it is the wavelength. We typically specify meters because we're working in the MKS system, meters, kilograms, and seconds. So the metric system. Frequency is in hertz. And speed of light is in meters per second. So when you go through and do your dimensional analysis, this is 1 divided by seconds. So you have 1 over seconds times meters is equal to meters per second. And everything lines up. So at least you basically got that right. When you draw your circle again, you go back to your basic formula. And I have found that this circle thing works really well. And that's why I teach it. So C, F, lambda, just like that. And because really C is the speed of light in free space, we can use 300. And again, there's an implicit million in there. We account for that by using this in megahertz. So this is in megahertz, this is meters. Then you just cross out the one you don't know, and you're left with the one that you do. You have the divisor bar, and you have the rest of the equation. That keeps you from having to go through and do the algebra and take this original formula, remember it right, and remember which one to divide by what, and stuff like that. And then you still end up making a mistake. Again, Ohm's law. E is equal to IR. E is electromotive force. I is current. R is resistance. And P is equal to I times E. We can draw it the same thing. P is power. I is current. E is voltage or electromotive force. Make your circle the exact same way, except that if you have P, I, E, and you don't know the one up top, this becomes a multiplication. Now, the one thing we did not add yesterday is the fact that this equation actually is not completely correct. E is equal to I times R. That's Ohm's law. Everyone agree with that?
Mm-hmm.
Okay. Well, as it turns out, resistance, R, is a special case. Resistance is the ability of something to resist DC. Impedance, which is the letter Z, is the ability of something to fight back against AC. In a resistor does not care whether it's seeing AC or DC. It makes no difference. So in a resistor, its resistance is equal to its impedance. Can everybody hear me okay, by the way?
Yep.
Okay, good. So for a resistor, they are equal. Now, remember we discussed the strange case of the capacitor and the inductor, right? The fact that a capacitor, and this is going to keep coming up over and over and over, is just two parallel plates. And for DC, it just hits a brick wall. And for AC, it appears as though it passes straight through. Now, this is actually really important because, as it turns out, for DC, the resistance essentially is very, very high. For AC, its impedance can actually be quite low. It can actually almost be zero. If I were to draw this as an inductor instead, what is an inductor fundamentally made of? Everybody, what is this?
Wire.
Okay.
Coil.
Does it matter really if the wire is a coil or a straight piece? Not really. It's still just a piece of wire, right? And a piece of wire that's a good conductor has what kind of resistance?
Zero.
Well, it's not zero, but it's low.
Close.
So for DC, an inductor is just basically a piece of wire. It is the fact that it has a magnetic field that it generates that makes it not so keen on allowing AC to pass. That magnetic field doesn't like to be stopped. So AC, it has a very high impedance. For DC, it has a very low resistance and therefore a low impedance. Now, the reason that I drew this is because this is our measure of resistance from 0 to infinity on this graph. So what is the lowest resistance you can have according to this graph?
Zero.
Zero. What's the highest resistance you can have according to this graph?
Infinity.
Infinity. Very good. Okay. Now, what it really turns out is that certain things don't play by the rules. Like if I were to draw this, what is this thing called again, everybody?
Inductor.
Inductor. Okay. An inductor is just a piece of wire, right?
Mhm.
So its resistance is actually here. But if we're looking at its impedance, so its resistance is about 0. But if we're looking at its impedance for AC, we already said that if we try to put a really high frequency into this, it'll develop a magnetic field that doesn't like to be changed. So what will happen to it? The impedance
Go
will be
up.
very big and it'll be something like infinity. Well, so clearly there must be something else at play here, right? Because this right there is not doing it. This is another axis called reactance, and it's the letter X. I think probably because they didn't know what other letter to use. So reactance can go from infinity all the way down to minus infinity. Notice you can't have negative resistances, at least not that we've not anything practical that we do.
Yeah, well, you can get, when you get down to kelvins, you can change resistance, right?
Yeah, but there's still no negative resistance yet.
Okay.
In theory, there could be, but so there's something at play here. And what it turns out is that there's this thing called reactance, which is the way that something reacts to AC. And it can be zero, it can be up to infinity, it can be down to negative infinity. So this is actually really important. So if anybody wants me to go through this like 16 times, I might resist, but I'll still do it. The reason that this is so important is because let's take a look at this inductor. This inductor, I'm going to change colors here, has an impedance of basically infinity at really high frequency. Well, since it's zero over here, it can only be one of two directions. It can either be way up here or way down here. And it turns out that its reactance is way up here. And just to be interesting, that it turns out is the inductive reactance of that device. What do you see in there that gets kind of messy in that little formula?
Pi.
Well, pi is just a number. I mean, I could replace that with 3 and it would still be pretty close. What do you see in there that's messy, everybody? It depends on the inductance of the device. That's not messy. It depends on 2 pi. That's not messy. But what's messy in there? What letter do you see?
The Z.
Now,
that?
XL,
What's this right here?
XL,
Frequency.
frequency.
Yeah. Uh-oh. Now we have a problem, don't we? What does that mean that our X is dependent on?
The frequency.
It's dependent on the frequency of the AC that's going through it. So if I do that, or I do that, or I do this, its impedance will change. Uh-oh. This is actually really profound and super important because sometimes the impedance will be up here or the reactance, and sometimes it'll be here, sometimes it'll be here. Sometimes it'll be off this scale. Well, okay. So it turns out that an inductor does in fact have a positive reactance. So now we're going to draw the other thing. And what's the other weird analog device? Kind of like the opposite of an inductor?
Resistor. Oh, capacitor.
Capacitor. One stores energy in a magnetic field. This one stores energy in an electric field. Right? Well, okay. We also have something called XC. Capacitor, if you think about it, because really it's just reacting to the charges that are being applied to it, will shift back and forth. And the faster and slower it changes, the faster and slower it responds. Well, that means that it appears to be different depending on frequency. Uh-oh, there we go again. It's dependent upon frequency. Formula for that is 1 over 2 pi fc. For this one, it was 2 pi fl. For this one on the bottom, it's 1 over 2 pi fc. What's the messy thing there? What's that? What's the messy letter in there that changes things? Frequency again. But this time, where's the frequency? On the top or on the bottom?
Bottom.
On the bottom, which means that if the frequency is really high, the bottom goes to infinity and the whole thing goes to 0, which means that a capacitor will have something that is negative down here. And it changes depending on the frequency as well. So if I have a capacitor and an inductor in the same circuit and no resistance, here's where it gets really amazing. All right. And I do mean this is amazing. So I am going to draw a simple series circuit. What does series circuit mean, everybody? What does it mean if something is in series?
Everything's in line.
Everything's in line. Yep. Good. Okay. This is a simple series circuit. And I have ZL and ZC. And it turns out that capacitance, ZC, is negative 1 over 2 pi FC. And ZL is 2 pi FL. And our letter Z and our letter X for that matter, these are both measured in ohms. Nothing confusing about that, right? Isn't resistance measured in ohms too? Yeah, okay. Impedance and reactance are also both measured in ohms. What happens is the Z, when you take it, it puts a direction on it. So the capacitor goes down this way and the inductor goes up this way. And so now we are in a situation where we simply add our impedances together. Well, that's ZL plus ZC is 2 pi FL plus negative 1 over 2 pi FC. Okay. And I know the writing's getting a little small there, but given the fact that one is positive and one is negative, and the capacitor C and the inductor L, the values have been selected, could I select a frequency F where they completely cancel each other out?
Probably.
Yeah, you can.
Yeah, I'd say yes.
The answer is yes. And in fact, this is a super important part of electronics because that frequency is 1 over 2 pi square root of LC if we go through and do the math. And this is known as the resonant frequency of a circuit. And why is this so important? Because if I subject this circuit to a whole bunch of different frequencies that are coming out of that device, this will exhibit a different impedance for every one of those frequencies. So each frequency, if I were to draw this on a graph, let's say I have a frequency that's 0 all the way up to infinity. And every so often I'd pump out a frequency on this chart. What does it mean if each of those frequencies experiences a different resistance to flow? Is there going to be one for which there's basically no resistance to flow? That formula says yes. So let's say that formula says yes, and this is the frequency that gets through. And for everything else, it goes like that. Super profound. What does this mean? What does it allow me to do if I have that whole range of different frequencies there?
Tune the circuit.
I tune the circuit. I can pick the frequency that comes out the other side.
What's the practical application for that?
You got a filter on your guitar?
Mm-hmm.
There you go.
Gotcha.
This is a frequency tuned circuit. This allows you to filter things. If anybody has ever listened to a stereo system and you have a three-way speaker, for instance, where you have a tweeter, a mid-range, and a woofer, what is the point of sending super high frequencies to the woofer?
There is no point.
There's no point. So what you do is you filter them out before you even send them, because there's no point doing it. The same with the tweeter. If you were to send low frequencies to the tweeter, they would do absolutely nothing. So you filter them before you do it. What if you have a circuit where you are listening to somebody's voice, and so their voice has a profile that looks like this? So we have our zero frequency, and let's say 3000 hertz. And there's something right around here that is like a noise spike. There's some annoying sound in the room. You don't want to hear it. You would build a filter that would do this. And what devices do you use to build that filter?
Compressor.
Capacitors and inductors. Capacitors and inductors, because of their ability to behave differently at different frequencies, are the basis for tuned circuits. Without tuned circuits, we would basically be in the dark ages. We wouldn't be able to build anything that had any kind of frequency dependence. And since a lot of our work in the world uses AC, including radio, including audio, including cell phones, including computers, none of that would be possible. Capacitors and inductors are the basis for everything tuned. So, as it turns out, does everybody remember the Pythagorean theorem? Come on, thinking back to middle school. Does everyone remember the Pythagorean theorem?
A squared plus B squared equals C squared.
Yep. Okay. Excellent. A squared plus B squared equals C squared. Okay. Well, as it turns out, we have resistance and we have reactance, the letter X on the perpendicular axis. The impedance, here's the X. Sorry, here's the R, here's the X. Z squared equals X squared plus R squared. Or Z, impedance, is equal to the square root of R squared plus X squared. Interestingly now, E equals I times R no longer applies, does it? E equals I times R is actually just a special case. The formula is E equals I times Z. But what do you notice about Z? Does it lay flat on the x-axis? Or does it have an angle?
It's going up.
It's turned up at an angle. It could also point this way, depending on the angle. Well, if I have a current I, and the current looks like this, and then I have an E and a Z, and I see that my Z has an angle associated with it, and remembering that we have that circle, and our current can really be measured as something going around and around a circle, making a sine wave. Well, as it turns out, what this does, if I have a positive angle, like on the above right there, if I'm left with a positive angle, what I end up with is that my voltage E is equal to my current times the magnitude of my impedance rotated forward by that angle. And what I get is that if I were to look at this in time, I'd have one graph that looked like this and another graph that would look like this. This would be my current and this would be my voltage. And this spacing, that difference, would be equal to this angle. And this is called a phase shift. So inductors and capacitors actually do all this cool stuff. When you get to your general exam, when you get to your extra exam, this is super important. When you get to your
When you see that in the Z in a formula that has the angle on it, how is that written? How do you see that in the formula?
Okay, so typically what you'll see is it'll say Z is equal to 32 ohms, and it'll say like 30-degree leading. Or it'll say that would be a magnitude. You can also see it written as 11 plus J20 ohms. And that means it looks like this, 11. And the J means it goes up, positive J, 20. And from there, you can figure out what the angle is. That's trigonometry. Does that answer the question?
Yep. Thank you.
So this would be inductive. You'd know just by looking at this that that would be inductive. If somebody said that it was 11 minus J20 ohms, it would be this way, and that would be capacitive. And the reason we know that it's capacitive is because the capacitive has a negative sign on it.
So is there a point where this could cancel out your signal?
Well, when you say cancel out the signal,
The phase.
oh yeah. So let's say we did this. Right? We have this, and we have a capacitor on the graph that goes purely this way, and we go with the inductor purely that way. The exact same magnitude of impedance. What's the total resistance?
0.
Yeah, and what's the total impedance? Or what's the total reactance? It's also 0.
0. Yeah.
And yes, it is square. Yeah, the magnitude is square root of r squared plus x squared, to answer the question that was just posted. So this is actually really important, because if these are now in phase, right? If these are now in resonance, as it's called, the phase shift that they create is quite obviously probably 0, right? So 0 phase shift, in addition to being purely passing at a given frequency. So again, the pass band will look something like that. Really important too is the fact that I could draw it like this.
Looks familiar.
Right? And this would be a parallel circuit. I could draw this as a parallel circuit, in which case what ends up happening is at the resonant frequency, I end up with this. What would I ever want that for? Why would I ever want a notch cut out of something?
If your signal was in that notch, then
If there was a signal in that notch, yeah, exactly. Or we'll say an offending signal was in that notch that was getting in the way of you
Excluded.
being able to understand something. Okay, one more. Why would I ever want something that looked like this? And I allow all those low frequencies to pass.
Exclude the upper
Why would I ever want that?
interference or
Mhm. Or why would I ever want this? Why would I ever
the
want
up.
that? That
Yeah,
would be
the
the
high
opposite.
frequencies.
let's
So-
say that let's say that I had like my power supply was noisy. It made a sound. Well, this could filter that out. The same way that if I'm drawing a power supply, I have something that looks like this. This is actually one of those things in the schematic. And yes, these are called low pass, high pass filters and band pass filters.
Mm-hmm.
So if I have something that looks like this, and here's a
Diode.
diode, and then I have this.
Right.
Okay, there's a capacitor. And I'm going to put a Zener diode here. And here's my load. All right, so I have AC and AC here. What comes out of my diode? Again, we did this yesterday.
Directional.
Yes.
Oh,
Only the positive part comes out of my diode, right? So this gets knocked out. And so what I end up with is the stuff on top. So what's up there looks like this. If I were, and that's in time, if I were to convert that to a frequency representation, it would look something like this. You have some here and here and here and here and here. What do I want this to be over here? What do I want to come out? What is the point of building a power supply?
You want direct current?
I want DC. Does that frequency, if it's from 0 to infinity, what's the frequency of DC? DC has no frequency, which means that all this other stuff that exists as a result of that wave looking like that needs to go away. Needs to disappear. I need to make it gone, or else I get a noisy power supply. So what the capacitor does, the capacitor has a frequency response impedance of 1 over 2 pi FC. So as frequency goes up, what happens to my impedance?
goes down.
Goes down, which means that it's a better and better path for all of that crap. If I can basically suck all that stuff down and make it go to ground, does it ever make it out to the end?
no.
Nope. This is a low pass filter. It's permitting only the low frequencies to go through. The end result is I end up with something that looks like this, which is a lot cleaner than it was. Has a lot less in the way of high frequency components. That is one of the reasons that we do all this filtering. We do low pass. That's a low pass. Do high pass. And we do band pass. That can be very narrow or very wide depending on the components that you use.
Is this the same that would be used in a audio compressor? The
Yes,
same.
similar to it.
So bottom line, this these filters and whatnot, they enhance your signal noise ratio.
Yep. They allow you to pick the frequencies that you want and reject the ones you don't. That's the whole point of filtering. Okay. Well, now that we've hopefully not confused everybody completely. This is a good time to speak up if you are a little bit confused by this. Because this is fundamental stuff that is not necessarily on your exam. But part of the point of this class is to teach you the fundamentals, which is, an understanding of why this stuff works.
I have a question about I missed yesterday, so I'm sorry about that. But the electromotive force,
Mhm.
what exactly is that? I heard you say voltage, so it's in volts?
Yeah.
Well, like what are the units? Okay.
Volts. And that's why we
So
use the letter E.
so it's not it's okay. Okay. Cool. Sounds good. So you could rewrite the equation Ohm's law V equals IR. It's the
Yeah.
same.
Yes.
Okay, cool. Cool. Thank you.
Mhm. Okay. Any other questions about that before we move on?
Yeah, so I sort of understand the low pass, high pass, and bad pass stuff, but could you just go over it one more time and explain it like I'm 5?
Okay.
Thank you.
Okay. So we have this is our frequency chart. We start at 0 up to infinity. So 0 frequency would also be known as DC, and infinity is, infinity. But this represents, what types of frequencies exist. This one might be here. This one might be way up here. This one, low frequency, might be way down here. And one thing that's important to note is that all of these frequencies can and do coexist. They can be added to each other. Like you can have a signal coming out of an AC source, right? So this is AC. You can have a signal coming out of an AC source that consists of an amplitude of 3 and has a frequency of, let's say, 1,000 hertz. You can have an amplitude of 2 at 2,000 hertz and an amplitude of 1.5 at 2,500 hertz, right? These are just audio frequencies. But basically on an audio spectrum, on a spectrum chart that looks like this up top, you will actually have a spike at 1 kilohertz and one at 2 kilohertz and one at 2.5. And they'll have amplitudes that look like this. Now, if I were to look at this in the time domain, which is looking at how this frequency looks in time, like if I had an oscilloscope, I would see something that looked like this. It'd be all over the place. You could look at it and not know what it is. But if you were to break it down into its frequencies, you would see that it had a component at 1 kilohertz, one at 2 kilohertz, and one at 2.5 kilohertz, along with their amplitudes. So this is the time domain, and this is the frequency domain. This is why we do something called spectral analysis. Because if you look at a time chart, like you look at you look at a representation of your own voice in time, it's a mess. You look at what your voice looks like, but if you look at a frequency analysis of your voice, you'll actually be able to break it down into individual components of frequencies. They are all added together. What that allows us to do is understand that if we want a low pass filter, we can pick our components so that, let's say we want everything from 1 kilohertz up to 2. That would be a low pass filter with a cutoff around 2 kilohertz. If we just wanted the frequencies above 2 kilohertz, we could do this. That would be a high pass filter. If you put a high pass and a low pass together, you see that gap in there where they're both on? That becomes a band pass. essentially adding them together. So a low pass followed by a high pass could make a bandpath.
And time domain allows for more people on the spectrum.
No, time domain is just time domain is the real world. We think of things in time. I mean, you can't really do all filtering is really done in the frequency domain. The time domain is just how we see things. So
why do we have so in the LMR world that I deal with, why do we have TDMA and
that's
FDMA?
different. That's different.
Oh, okay.
That's time. There's frequency multiplexing and time multiplexing. That's a different thing.
Okay.
Because time multiplexing is when you split a time and you instead of having a continuous signal in that's assigned to one channel, let's say two different groups of people will get different time slices, and you'll turn off the receiver during the other time. But they still have, frequency spectra. They're still operating on the same basic frequencies. So other questions on that? Chris, did that make sense? Little?
Yeah, that was really helpful. Thank you.
Okay.
I got a silly question if I can ask it.
Oh, I like silly questions because they're usually
Okay.
not.
Is there anything in ham radio that would be the equivalent of a graphic equalizer?
Yes.
And
And
what
in
is
fact, we do pre-emphasis on our audio. Exactly that. We tailor our audio passband for enhanced receivability on the other end. So I actually have a very annoying very annoying sounding microphone, which is called the Heil. It's an HC Ford. I think it's called the Dream Element, the DXer's Dream, and it's really annoying. And the reason it's so annoying is because it has a frequency response, which goes from like zero, instead of like from 0 to 3,000 hertz, which is audio peak, and being flat across the whole passband, which is typically what you get. My headset with my microphone with that element in there has a passband that looks like this.
Ugh.
Oh, it sounds horrible. And it has enhancement from about 500 hertz up to about 1,500. I'll say about 1,200.
So it's not just that you've been sick.
Well, no, that's not the one I'm using.
Okay.
This is the one but this is it's called my DXer's Dream element. The reason that they call it that is because when you get on the air, the low frequencies and the really high frequencies aren't the ones that punch through. Those aren't the ones that get heard on the other end. So it does a pre-emphasis and it peaks those frequencies that are going to do you the most good. But yes, we do that.
I had a question about the equations for when we were doing here, I think I have it written down.
Cute dog, by the way. Or dogs.
Thank you. One of them's got a Christmas sweater on. When we were trying to find the frequency value that would cancel out and allow us to keep tuning, I'm kind of confused about how the equation
Here we go.
responds to the analog thing.
Yep, here we go. Okay, so I'm glad you asked. Okay, these are going to be in series. So we have ZL and ZC. Here we go. Looking at the total, Z total is ZL plus ZC. They add in series. This is 2 pi FL minus 1 over 2 pi FC. And if you do complex math, actually, if there's a J or an I in front of it, which means that it's up and down. So now we can go through and set those to 0. We can say we actually want a situation where they cancel each other out. So then we end up with 2 pi FL minus 1 over 2 pi FC equals 0, or 2 pi FL is equal to 1 over 2 pi FC, and then we solve for F. And from that, we get F is equal to 1 over 2 pi square root of LC. And this is known as the resonant frequency. Okay, said it. Does that make sense?
Yeah, that makes sense.
Okay. And this shows up all over the place. A really important thing, because we actually not only use this stuff for building filters, we also use it for making oscillators. So by picking capacitors and inductors, we can actually generate frequencies as well.
Okay, I think the math makes sense. I think what I'm kind of struggling with is how we use it in a physical device.
Oh, okay. Well, so let's say that you have picked. Okay, so let's say that you've now picked. I'm going to just draw a new chart. Hold on. Okay, so let's say you've actually built this. And your frequency of resonance is 1 over 2 pi square root of LC. And you've chosen that to be 1,000 hertz. You've chosen L and C. There's your L, and there's your C. You've actually selected them so that that value is 1,000 hertz. Now, you hook this up to your audio, which comes out, and it looks like this on the frequency spectrum from 0 to 3,000, let's say, and it looks like this. What frequency would you pass it when you pass that signal through your filter? What frequency is going to be the most enhanced?
Would it be 1,000?
It would. So you're, instead of this, what you're going to end up with is something that looks like this. It allows you to pick a particular frequency and work with it.
Okay, that totally makes sense. Thank you.
And here's a really good practical application for it. You ready? Here we go. I'm going to open up a picture of this, and hopefully there's a good picture inside. There we go. Let me share it. Okay. We're going to go there and hope that this is when you go off script a little bit. There we go. Can everybody see that really nice photo?
Mm-hmm.
That is the inside of an antenna tuner, which is an impedance matching device. So what do you see? Everybody tell me what you see in there.
Capacitors.
How many capacitors?
1, 2, 3.
Only 2.
What's the third on the bottom?
The third is a big fat inductor. That's a big coil of wire.
Oh, okay.
And notice it's got little solder blobs on it.
Yep.
Those are switchable. So you can pick the amount of coil that is in play. Why would you ever want to do that?
To change the impedance.
Here we go. Okay, this is a good segue into antennas. This is a dipole antenna. now that we've covered impedance, a dipole antenna is a half wavelength long at whatever frequency you've picked. If it's a half wavelength long, it has an impedance of 72 ohms. This is my radio down here, which has an output terminal, and it has an impedance that it looks for of approximately 50 ohms. Okay, is 50 equal to 72?
No.
It is not. So I'm going to hook this up to feed line, which is basically either two parallel wires or coaxial cable. That's 72 ohms. And I'm going to run this down to here. What is the impedance of my output circuit? It's 50 ohms. The impedance of my antenna is 72 ohms. This is called a mismatch. What will happen is if I try to pass energy out into the world, some of it will go out and some of it will bounce back. And when it gets here, power and energy, what do we know about energy? Can neither be
destroyed.
Can it be neither be created nor destroyed? It just changes form. What is the most common thing for energy to be converted into?
Heat.
And
And what happens if you start to heat up your transmitter circuit?
Burn out.
You let the smoke out. That's right. Heat is the enemy. So what we do is we have an impedance matching device, which we insert in between, which looks, oddly enough, like this. And what do you see in that box?
An inductor and capacitors.
Okay, so we have inductor and capacitors. This antenna is 72 ohms, and it is now in series with a capacitor, which we can tune. If we go back to that photo, we will see that you can actually tune that value. You can actually then tune the inductor value and tune the second capacitor. And the overall goal is to do what?
matching.
Make it look like 50 ohms. Through the magic of adjustable circuits, adjustable capacitors, adjustable inductors, we can do that. And what that allows us to do is, and it looks just like that. Those capacitors, those are actually rotary. You can see the one on the right has actually been partially engaged. The one on the left is engaged to a different amount. The amount of parallel plates that you have engaged with each other determines what the capacitance is. If they're completely disengaged, they have no capacitance. If they're completely engaged, they have full capacitance. And because they can turn, everywhere in between is everywhere in between. And by changing those values, go ahead.
No, I was going to say, it kind of resembles the old television tuners.
That's exactly what was in the old television tuners. It's exactly how you tuned them. Same with old radios, old shortwaves and stuff. Okay, so now we've done the magic of tunable circuits. Yay, everybody. Well done. So, okay, so the way that schematics are drawn, see, I didn't know. What I love about teaching this stuff is I never know where we're going to end up on a given day. I mean, I have a basic idea, but I never really know. Okay, this is a resistor. If I want to make this a variable resistor or a potentiometer, I will do that. That's often usually tied to a tuning knob or an adjustment knob. Most likely place to find one of these is in a volume control. I can take an capacitor. I can do that. That makes it a variable capacitor. I can take an inductor, and I could do that. I could also do it like this, and that makes it a variable inductor. And in the case of that one that we just saw, the variable inductor, actually looks something like this. And each of these is then tied to a switch, a position on a switch. And by changing the switch position, clunk, 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 that allows you to change the amount of coil that's still left in the circuit. So adjustable stuff. Okay, so now we're into schematics a little, but I'll tell you what, before we do that, we're going to do one more thing and then we're going to take a break. Because we are on page, if you're curious, page 15. We're jumping around a little bit. The first part of this book, I find it doesn't necessarily follow the order that I would like it to follow. So, okay. What I'm going to do is draw this capacitor. And say, okay, so this is a capacitor. And what is the symbol for how much capacitance? It's called the F. What is that again?
Farad.
Named after Michael Faraday. And this is an inductor, letter L. And the name again is the big letter H. Anyone remember that one?
Mm-hmm. Harvey.
It's a Henry, named after another scientist. Okay, so it's important to note that 1 farad is huge. 1 Henry is also huge. We almost never talk about a capacitor or an inductor being a single unit in size because they're enormous. They're huge, huge values. So what we do is we start to use our prefixes. And these are used all throughout electronics because we typically talk about things that are a lot smaller. You start with M for milli, which is 10 to the minus third, which is you start with a 1 and you go 1, 2, 3, 0.001. So 0.001. And then we have micro, which is 10 to the minus sixth. Start with a 1, 1, 2, 3, 4, 5, 6. So scientific notation, is everyone familiar? Is everyone comfortable with scientific notation? And it's okay if you're not. Tell me if you're not.
So
What a lot of people forget is that 1 is also a placeholder.
Yes.
So they tend to add the zeros. How many zeros are in that to minus
Okay.
6 zeros? No, it's the 1 is a placeholder too.
Okay. So scientific notation is just basically 10 to the something. By convention, if I have 10 to the third, that exponent is 10 times 10 times 10, which means 3 times is 1,000. It turns out that 3 also translates to 3 zeros being there. If I were to have 10 to the minus 3, let me use a different color. By convention, anything to the minus power is 1 divided by that. So it's 1/10 times 1/10 times 1/10 equal to 1 over 1,000 is equal to 0.001. Notice that we have -3. There's a 3. The 1 is, in fact, the placeholder because the 1 is what's important. So we start with a 1 and go 1, 2, 3, and then fill in zeros. So as you were saying, make sure that if you're going smaller, you're not going to have the same number of zeros. You're not going to have that, 3 zeros. It's going to be 0, 0, and then 0, 0, 1. So, okay, so we now have micro, we have milli, micro, nano, and pico. Those are the most common ones as we go smaller. This is 10 to the minus 9th, 10 to the minus 12th. I could draw, let's see. Using up my ink. Okay. So those are our much smaller than 1 things. Milli and micro, often millihenries, microhenries. Right? We have our inductors that are in millihenries and microhenries. We also have capacitors that are in microfarads, and we typically don't use nanofarads. Instead, we just use picofarads. We also call them puff. So you could have like a 220,000 picofarad. It would be the same as 0.22 microfarad, just by moving zeros around. You could have a 10 millihenry coil, or you can have a 3 microhenry coil, for instance. So those are the most common things that we see for the really small things. But now we also have really big things. So let's take a look at our frequencies. Right? We have all the way from 0 up to infinity. Well, typically below 1 hertz, we really don't deal with that kind of thing very much. But we deal with like 1,000 hertz all the time. Well, the little letter K, that's a kilo. That's 10 to the 3rd or 1,000. So this would be 1 kilohertz. 8,000 hertz is 8 kilohertz. Okay, so we use that all the time. Use those are audio frequencies. When you get your hearing tested, that's how you get your hearing tested. It's measured in kilohertz. Then we have big letter M, which is mega, which is 10 to the 6th, which is a million. And we start to deal with hertz again, megahertz. So if we have 82,000,000 hertz, well, we have 1, 2, 3, 4, 5, 6, 82 times a million. And we just established that a million is mega. That would be 82 megahertz. We also would say that if we took, let's say, 1 0 away from that, we want to count zeros. 1, 2, 3, 4, 5, 6. 8.2 times a million. That would be 8.2 megahertz. And then we have above that giga and tera. This is giga's 10 to the 9th, tera's 10 to the 12th. All right, how about a 5-minute break, everybody? You know what, let's make it an 8-minute break. So 9:40 my time. Does that work?
Works.
All right.
You know. Oh, you're here. You know, I was just Is it raining? No. It's pouring already. I know, it's slow. Go do it, I'm fine. Of course.
All right, is everybody back? Has everybody returned?
Yeah.
Can anybody
I'm
hear
here.
me? Can anybody hear me? Is there anybody out there? If not, if you can hear me. Is there anyone
Scott.
home? Yes,
Bruce here. You got my message early today?
I did. Yeah.
Yeah. Oh, well,
Yep. It's a start. It's a start.
it's a start. It is a start. What are we're looking at what? Is that your radio? No.
Nope. This is WebSDR and this is the WebSDR and University of Twente in the
Oh.
Netherlands.
I've been using the Utah Web SDR.
I do too. Have you ever listened to have you ever listened to yourself?
I listen to myself and
Yeah, it's pretty cool, isn't it?
you know, and it's it's probably cheating a little bit, but sometimes I use it to help pick out a call sign when I can't quite catch the call sign on the air.
Mm-hmm.
You know, and I have a little mini mixer, and I can keep the website running, and I can dial up the audio on the website or dial up the audio on my radio through the same speakers.
A little cheating. It's kind of half cheating. All right, everybody back. 9:40. Okay, so we're going to be doing a little more filtering. I might as well do this now while I'm thinking about it, though. All right, it took a minute to set it up. So what we're looking at is a frequency domain chart, frequency domain graph called a waterfall display. This is in kilohertz. We could move the zero around 14.015 megahertz. This is out of the Netherlands. This is just an SDR, which is a software defined radio, which basically looks at what's coming in through the antenna. And remember I said that actually what you're able to hear, frequencies can all be added together. This is a single antenna and it's all split. Nice cat, by the way. And it's all split into its component frequencies. And this is what it sounds like. Notice that you can hear different pitches with your ear, right? They're all there. There's only one antenna. Your ear is good at splitting things into different tones too. Okay, so now when I talk about filtering, we are adjusting the low pass and high pass ranges of this filter. Now notice what happens if I move this out of my pass band. Where'd he go? Where'd the signal go? It's now above the pass band in my band pass filter. If I move it,
it's just outside.
it's still there. You just can't hear it. I can do the same thing by going the other way. This is why we do filtering.
This looks a lot like what I used to deal with in the military. I was an acoustic analyst.
Yep. Okay, so now what we're going to do is we're going to take that same filter and we're going to move it up here. Any guess what that is? Anyone? Any guess?
Voice. Yeah, voice. Sounded complicated.
Yep. So why was it that let's filter down. Why can we hear so little of this? Why?
It's a
Why does it
broadband signal.
That's right. We're
Signal.
missing most of the information. So filtering is used to trap the appropriate number of the appropriate range of frequencies to actually be able to discern what is in a signal. Anyway, this is available free on the web. It's pretty cool. There's SDRs all over the world. So notice we were playing with high pass and low pass, and good way to get your hands on it firsthand. Okay, so now what we're going to do is we're going to talk about bigness of things. And an easy way to describe things that are really big and really small, because big numbers, like if I were to tell you that something was this, if I were to tell you that something was that many times bigger than something else, does that really matter? Couldn't I just say that it was about this many times bigger and still be mostly right? What do you think? I mean, unless I really needed to be exact, it's about that many times bigger. Well, okay. So at some point, our precision really doesn't matter so much. What's important is the order of magnitude. So if I were to look at this number and represent this another way, I could count, here's the decimal point, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it would be 1.235 times 10 to the 10th power. That's a pretty big number. We've already established that's a pretty big number, right? So let's say that I had an amplifier that made things that many times bigger. I could
That's
say
a
that
lot of
this,
power.
I could say, oh, it depends. I mean, what if I was dealing with picowatts coming in? Then it's not a lot of power. So let's say that I was dealing with this much amplification. Well, okay, that's kind of dumb. It's kind of dumb to look at a number like that and actually try to make some sense of it. However, what's not dumb is to say that it's approximately that times bigger. What's even less dumb is to say, okay, does everyone know what a logarithm is? Or an exponent? Raise your hand if you're not familiar with those. I'm sure that some people are going to say they're not familiar with those. Okay. Well,
More familiar with the bottom than the top.
Okay. So these are inverse functions. An exponent is something that's a base to an exponent. This can be 2 to the 10th. This can be 10 to the 4th. You have, basically, this means your base is raised to this power. 10 to the 4th would be 10 times 10 times 10 times 10. 2 to the 10th would be 2 times 2, 10 times. The reason we do this is it's a really, really good way to do shorthand notation. It makes things a lot easier and a lot faster. And the other cool thing about it is that if we break things out into their component, into their basic essence, 10 to the 4th times 10 to the 6th, we could write that out as all those tens. If the bases are the same, you can simply add the exponents. Really quick. And again, we could write it all out and break it out into tens. 10 times 10, 4 times, times 10, times 10, 6 times. And we count them and we see that there are 10 of them. Therefore, it must be 10 to the 10th. So that's our shorthand notation. Now, what's interesting about this is that we can also say, let's take any number, 162. Can we say that that is 10 raised to the somethingth power? Actually, yes. It might get a little bit messy, but for the most part, yes, we can raise 10 to the somethingth power and get 162. Well, we already know some about this. What's 10 to the 0 power is 1. 10 to the first power is 10. 10 to the second power is 100. And 10 to the third power is 1,000. So we already know a little bit. What would 162 be? Somebody give me an approximate.
1.62 times 10 to the second.
Well, yes, it would be, but somebody give me like 10 to the somethingth power. is 162? Somebody just guess. If 10 squared is 100 and 10 to the third is 1,000, what do you think 162 would be? Just give me a guess.
10 to the 2.6.
Okay, let's just start with 2.6. Okay. It's probably a little high, but okay, so you get the basic idea. Well, it turns out that we can do something called a logarithm, which is the inverse of this. So we can take the log of both sides, say the log base 10 of 10 to the something is equal to the log base 10 of 162. We're doing the same thing to both sides. The log is the power to which 10 has to be raised to get something. So the log of 10,000, to what power would you have to raise 10 to get 10,000?
10.
Would be 4. Because 10 to the fourth is 10,000. Okay, so what would the log of 1,000 be? That means 10 to the something
3.
is 1,000, and that's so that would be 3. Okay, so this is where we've just done a little inversion here of this function, and we've said, okay, well, we don't know the question mark, but if we raise 10 to the something, and then we say what power did it have to be raised to get it, the answer is just the something. So there we go. And now we can go to our calculator. Everybody's calculator has a log function. And when I go and share my calculator, you will see that even on Windows. And somewhere there's a log button. Everyone see the log button now? Down at the lower left, 162. And I go log, and it's 2.21. So guess what? The log of 162 is 2.21. The log of 1,000, and it better be 3. The log of 10,000, it better be 4. The log of 1/10 by convention, it's a negative number. It should give me -1. The log of 0.000001, this is a millionth. That should be -6. There it is. Okay. So what we now have is this thing called the logarithm. This is also how earthquakes are measured in strength. That's why a 7 is a much bigger earthquake than a 6, and an 8 is a much, much bigger earthquake than a 7, and a 9 is a huge earthquake compared to an 8. Because they're powers of 10 bigger. Okay, so now what we have is my handprint. We have this log base 10 of something. Well, this is great, but it doesn't really give us that much knowledge unless we do something with that, what's in a question, with that question mark. What we can do with this is we can do ratios. We have an end and a start. This allows us to tell what the difference is between the endpoint and the starting point. How much bigger or smaller is the endpoint than the starting point? So let's say we go through a power amplifier that gives us a gain of 50 times. So that means we have 1 unit over here, and we end up with 50 units over here. So we could say, how many times bigger is that? Well,
High.
agree, it's 50 times.
Yeah.
Now, let's say we put this through another unit that is 125 times. And then we put it through another one that's 11 times. But then every time it goes through one of these little cables connecting it, it goes down by a factor of 1/10. So it's 0.9 times. And this one is a little worse, so it's 0.8 times. And this one is 0.9 times. This is looking like a little bit of math now, isn't it? You got to do a lot of multiplication to get the answer. Oh, we can do that. I'm going to do that. So 50 times 0.9 times 125 times 0.8 times 11 times 0.9 is 44,550. So the real question is 44,550 really much different from 45,000? Is it really much different from 42,000? I mean, it is, but it isn't. What we really care about, again, is the order of magnitude. How much bigger is it in an order of magnitude rather than an exact number? And this is where the logarithm comes in. So we know that if the end result is 44,500, we can take the log base 10 of 44,500, or sorry, 550. See, there's already too many numbers to deal with. And I'm plugging it into my calculator and find that the answer is 4.65. Well, conveniently, I could also do the same exact thing on each of these little units where I take a multiplication and I could just add them together. Well, as it turns out, because we're working in the exponent world, well, as it turns out, this has a name. Anyone ever seen this name before? Add an extra letter to it.
dB.
Hmm?
Decibels.
Decibels. Well, this is from Alexander Graham Bell. It was determined, he determined, you know what, we're going to create this unit, which is an order of magnitude unit for describing how much bigger things are than other things, when the things are really big or really, really tiny. There was a little bit of I'll call it repair done with the unit, because it turned out that it was a little bit too small. So then we multiplied it by a factor of 10. That gave us something called a decibel. Anyone ever heard of a decibel?
Mm-hmm.
That's probably pretty common, right? But that's in the common vernacular. People know what a decibel is. It's a measure of how big something is, how loud something is. Usually we think of it as audio. You know, what's a degree of hearing protection that you need if you go into a noisy place? How loud is an airplane engine if you're 3 feet away from it, et cetera, if you don't get sucked into it? That's known as a decibel. But the thing is that a decibel is a measure of how much bigger something is than something else. So in the case of audio, it's compared to something that the average person can just barely hear. And it's a measure of how many times bigger it is. So now we can take a look at this thing and say, well, okay, so let's look at each individual one of these little audio amplifiers or components in here, and we're going to erase this stuff, and we're going to take that value, which is log base 10 of the question mark, and we're going to just write our formula. dB is 10 times log base 10 of the endpoint divided by the starting point. And again, we got this is 44,550. And that ended up being 4.6. 4.65. And that was in bells, but now we have to multiply that by 10. That is 46.5 dB. That is our gain provided by this whole system. What is really convenient about decibels is now I could go and I'm going to take 50 log times 10. I get for the first component 16.9 dB. And then I have a 0.9. I get negative 0.5, negative 0.5, negative 0.1. And for this one, 20, that's 21 dB. And for the 11 times, I get 10.4. Okay. So if I were to take all these and add them together, I would get 17 plus 21 plus 10.4 minus 1.1. And I guess I did something wrong in the math somewhere. Oh, I see. I got 49. Let's see, 50. 25. 21, 11. Okay, so you're actually seeing the benefit of doing this already because apparently I made a mistake somewhere. 50 times 125 times 11 times 0.9 times 0.9 times 0.8. Okay. So I did something wrong in my math somewhere, but the point of all this being that now instead of actually saying like having to go and buy a component that has a certain decibel gain or loss, when you buy something off the shelf, the decibel gain or loss is actually specified, which means that each of them can be basically done independently of each other. You can buy them independently. You can build your system independently, and it's a really nice piece of shorthand. So there are two things from all this that you truly need to remember. Ten decibels is 10 times. 3 decibels is approximately 2 times. Virtually everything distills down to that. That's it. That's what all this decibel stuff comes down to. So let's say that I have a starting power level of 3 watts and I put it through a magic box. And on the other side, I have 300 watts. What is my gain of this amplifier in decibels?
10.
Well, how many times bigger is the end point than the starting point?
100.
100 times. How do I get to 100 times? 10 times 10.
Times 10.
And I add my decibels together. So 10 times is 10 dB. 10 times is 10 dB is 20 dB. I don't care what's in this little black box. If somebody says it has a gain of 20 decibels, then it's going to give me that gain. If I see that I have this input and this output, I know that whatever was in that box has a gain of 20 decibels. The reason that this stuff is important to know is because decibels are universal.
Hey, Scott.
Yes.
I've always been a little confused on one aspect of this, and not so much this part. I get
Is it voltage versus power?
Yes. And when people talk about measuring a signal using a meter and measuring it in decibels, I struggle to understand that. I mean, volts I relate to. Volts is volts. I can conceptualize that. But when I'm measuring a circuit with a meter and I'm measuring it in dB, I don't know how to relate to that.
Okay. Here's why. We're going to use Ohm's law. Remember, everything comes back to Ohm's law. E equals I times E. E equals I times R, right?
Yes.
Okay. So we can rewrite this one as I is equal to E divided by R. Plug that back in. We get P is equal to E squared over R.
Yes.
Right? So that means that if we get a certain decibels here in power, what would the change be over here? It's the square. Because it's proportional to the square. So if you see a change in power, you're going to get twice as big of a change in decibels in voltage if you're measuring it. And it's because it's proportional to the square.
So if you have a meter that is calibrated in decibels, then it is basically following that equation.
Yep.
Its characteristic curve or response is tuned to that equation.
It's designed for that equation. But for the sake of what we're doing here, we're looking at power. So let's see. All right, what we're going to do is we're going to draw a simple diagram. Here's my transmitter. My transmitter has an output power of 1 watt. I run this through an amplifier, which has a gain of 10 dB. We have a coaxial cable, and we have an antenna, which is actually looking like this. It's a beam antenna, which by the manufacturer or by the design has a gain of 9 dB. We also have cable, which has a loss of minus 3 dB. The question is, how much power are we going to get out in the forward direction? All right, so somebody add those numbers together in decibels. We're looking at this section.
It's 19, so 16 decibels.
That's right. We have a gain of 16 dB. All right. Okay. How can I break up that 16 dBs into tens and threes? By adding them together. 10 plus 3 plus 3. Okay. Every gain of 10 decibels is how many times in power?
10.
Every gain of decibels of 3 times?
2.
Roughly 2. 10 times 2 times 2?
40.
I'll have an equivalent of 40 watts coming out the other side. And that's where the real power of this, the real power of decibels comes into play, because everything is specified in decibel. And you can just add them together.
We're getting into extra territory though, right?
You know, okay, so that actually brings up the next thing that I was going to talk about. The next thing I was going to talk about is, and I'm going to share this. This is actually on my list. Here we go. Why are we taking this class and why do you need a license? So for the next 5 or 10 minutes, everybody here, we're just going to talk about why are we taking this class and why do you need a license? So let's hear it. Let's hear it. Everybody here. Why are we taking this class? What do you think?
To prepare for the license exam.
That's true. Okay. Other stuff.
Learn how to operate radios.
Actually, no. That's a minimal part of it.
I wanted to
How to
learn
build
about-
the radios and antennas.
You can build stuff. Yeah. Okay. And what was the other one?
Oh, I wanted to learn more about how electronics work. that I use.
Excellent. Okay. Other stuff?
Well,
We have
like
not to
CC
do.
says,
you need a radio station license to operate on these frequencies.
That's also true. Yep. Okay. Keep going.
we don't
What
run
not
a
to do?
We
You
don't
want,
run
yeah.
a
Yes, I heard we want to know what not to do. That's good. What else?
so we
Oh,
don't
like-
Go ahead,
we don't-
Bruce.
we don't run afoul of the law.
So you don't run afoul of the law. Yep. Other ones?
Want to learn how to communicate when everything takes a crap.
Tangential to it, but yes. But that's a tangential response. Other stuff?
We don't broadcast on the wrong frequencies.
Actually, we don't broadcast at all. We transmit. We do one-way transmissions, but we don't broadcast. But yes, other things?
Because it's fun.
Because it's fun. Yep. Really, there's one reason, and I'm going to put it up here. One reason why we are taking this class. That is the fundamental reason why we are taking this class. So we don't hurt ourselves or anyone else in the process of doing this. So interestingly, if you look at other services, there are all kinds of guardrails that are put up. So does anyone do FRS? I have several FRS radios. Okay, what are the guardrails that are put up in family radio service?
Very limited power.
Very limited power. Good. Other ones?
Stay within the frequencies.
Well, and if you buy an FRS radio, you have no choice.
Right.
Other ones?
Limited antenna.
Very limited antenna, and it has to be permanently attached. Okay. Let's look at, does anyone do GMRS?
Before you go
Yeah,
to that,
go ahead.
some folks here may not know what an FRS radio even looks like.
Anyone have one handy?
They look like a walkie-talkie.
It looks like an old school walkie-talkie, but they're digital in most cases. They're 22 channels, and Chris went to go grab one. Okay, so FRS is Family Radio Service. It's an unlicensed service covered under Part 95 of the FCC rules. And so there we go. Okay, Chris. Let's see that FRS handheld. There we go. There's your standard FRS handheld. Permanently attached antenna. You have certain channels that you can choose from, and that's that. Right? It's completely safe for little kids to use. Right? And actually, they're almost foolproof, and they're also not that good. Right? We use them for neighborhood communications here in Eugene. Christian, you got your hand up, or is it Naomi? I can't tell. Okay. So that's FRS. Okay. Let's talk about GMRS. Who does GMRS? Okay. What are the guardrails up in GMRS radios?
I just got the license. So
Well,
it's,
right. Okay, you got a
Well,
license.
so power is the biggest factor, and you can change the antenna.
You can change the antenna and you can change the power level. But what are the other things you can't do?
oh,
Frequencies.
Right. They have specific frequencies. And when you buy a GMRS radio, they have channels that are programmed. Can you tune them anywhere outside of that range?
No.
No.
So those are guardrails, right? You have to apply for a license, which at least implies, there you go, at least implies that you went to the effort of doing something before you used it, right? Okay. What are the guardrails that are up in the ham radio bands?
License.
You got to get a license. How about anything else?
You gotta pass the test.
Anything else?
Or
Rules and regulations.
Rules and regs. Okay. Anything else?
Specific bands for specific rating, license.
Yep.
And modes.
Anything else?
Modes.
Is there anything about the equipment or antennas or anything that provides you that prevents you from doing any of those things?
No.
No.
There is nothing. Literally nothing exists to keep you from going outside those rules and regs and bands and stuff like that.
Grab
Except
the antenna
yourself.
and feel the power.
Like, are you allowed to build your own FRS handheld radio
No.
and use it? You are not.
No.
Are you allowed to build your own GMRS handheld radio?
No.
Are you
It's supposed
allowed
to be certified?
Are you allowed to build your, that's right, and everyone has to be certified. Are you allowed to build and operate your own amateur radio, handheld radio?
Absolutely.
Damn right. How about your own amplifier?
Yes.
Okay.
Yes.
Are there rules regarding amplifiers? Oh
There's
yeah.
power ratings. There's power
No.
ratings.
There's all kinds of stuff. Are there rules regarding spectral purity of a handheld radio? I'm going to draw something here. So here's the desired frequency at which you operate. Right? Okay, so here's 0 and here's infinity. Let's say you want to operate on this frequency. If you buy an FRS radio, it can operate in this range. And every other, because there's no such thing as a perfect transmitter, everything else that comes out of that has to be a certain number of units down below the strength of the fundamental frequency in order to be legal. Any idea how that is measured? What units?
dBs.
That unit is measured in decibels. Exactly. When you buy something that has been certified for sale, it means that it has been tested to be verified that it's operating legally. But what if you're building something yourself?
I was going to say, except unless you buy it unless it was made in China somewhere.
Well, right, but we're not going there. But let's say you decide you want to build a handheld radio and or a mobile radio or any radio for that matter, and it's going to operate on this frequency. Who is responsible for making sure that it meets all those requirements that say that all the outside the band power, anything coming out has to be at least 60 dB below the fundamental frequency? Who is responsible?
You are.
You are. That's right. Here's the other one. And what happens? Okay, so what happens if one of your spurious emissions over here is not 60 dB down? It's only 35 dB down from the fundamental, and this happens to coincide with your local air traffic controllers.
Whoops.
You get a knock on your door.
You get a knock on your door. That's right. Okay, how about this one? We want to start with a 1-watt transmitter. And we hook this up to a piece of cable that goes like this. And we run this through an amplifier, which has 30 dB of gain. What will the output of that amplifier be?
1,000 watts.
1,000 watt. Legal or not legal?
Depends.
Let's say you're operating on the 2-meter band.
No, it depends on which license you have.
Any license.
Oh,
Technician and up, all cover that.
1,500.
You are
watts, I
legally
think.
allowed to run 1,500 watts. Okay. So now, let's say that inside this amplifier, this is a tube amplifier. You have an 8877 vacuum tube, which has 4 kilowatts of power dissipation available. Could you tune up this amplifier? Could you tune up that tube so the power level actually comes out at 2,000 watts?
Sure.
You could, but your legal power limit is 1,500. So you have to know how to not do that. Right? Okay. So now you run this through a piece of cable. If you're running, let's say, 1,000 watts. So your amplifier is just loafing along at a kilowatt. How much power does that cable have to be able to take?
It's 1,000 watts.
1,000 watts at least, continuous. Is there anybody telling you what cable you must use? So who decides?
It's all suggested.
Who decides what cable to use?
We do.
You do, because you're building your own station. Can other services build their own stations using their own components? The answer is no. Okay. So now you go up this tower, which you've gone through the process of getting a city permit for. And here's your antenna. And it looks like this.
And your neighbors love you.
Well, they might if you did a good job. Okay. And this antenna has a gain of 20 dB. What is 20 decibels? How many times?
100.
100 times. So whatever's coming in, its effective power in the forward direction is 100 times that. What did you have going into it? How many watts?
1,000.
What do you have effectively in that direction coming out?
Nice.
How many watts?
100,000.
100,000 watts. Legal or not?
No.
No.
It is. Your
The
transmitter
antenna
powers.
gain.
Antenna gain is fine, unless there's something saying you can't have an ERP, which is an effective radiated power above a certain amount. You're perfectly fine. You're not running over 1,500 watts. You can hook it up to any antenna you want. Why should you not point this at your neighbor's house?
Might fry somebody.
You might fry somebody, yeah. So here's the next question. Let's say that you're running this and you're pointing this up at the sky and you're trying to bounce signals off the moon. Legal or not?
Legal.
Yep. How about if you're trying to talk to trying to talk to the space station? This is way too much power to do that, but
Legal.
sure. Why not? How about if you're just aiming it along the horizon off into the distance from a hilltop and trying to use the 2 meter band to talk to somebody 700 miles away using some esoteric mode? Okay or not?
Yeah.
What if there's somebody with a house over here and while you're transmitting, they're watching TV and their TV goes out? Every time you key up the radio, their TV goes out. What do you think then? But let's say they're 5 miles away. Legal or not?
Legal.
Perfectly legal. Now, it may be that you have an agreement with them. You go talk to that, they come and find you and they say, look, you're wiping out my TV. It's like, well, you got a crappy TV. I'll try to help you. We'll try to work something out, but I am operating my station legally. So the question of why are we going through this class and why do you need to get a license now should be fairly obvious. Yes, it's great that we how to operate a radio, but that's not fundamentally why you're here. Fundamentally, it's so that you know how to build a station properly. When this ties into when stuff goes awry, you need to be able to operate. You need to be able to put a station together first. There are plenty of other services that can still operate, but there aren't a lot of people and services that can do a good job and actually figure out what to do to make things work right. That's really why we're here. And then again, to not hurt anybody and not damage anything in the process. Not interfere with anybody else. Stay within the rules and the regulations that give us the ability and give us the freedom to do all this cool stuff. Because this is some pretty cool stuff. But with a lot of responsibility, with a lot of abilities and a lot of permissions come a lot of responsibilities. So
some of those responsibilities are not regulated. They're more of a social responsibility.
Yeah. Anyone have any questions or comments about it?
There is one about your scenario there, and I don't remember if it's on this test or the general test, but there are some regulations about radiated power, in the vicinity of a human.
Yes. Oh, many. With great yes, thank you, Kai. Yes, and in fact, it's on this test as well. There are radiated power limits for people, and that's part of it too. We're given so much leeway that I like to tell people we are not appliance operators. That is not what this service is for. We can use it as that. And I actually had somebody tell me this class was the biggest waste of time that he'd ever had in his life. Because all he wanted to do was operate a handheld radio. I said, well, there are lots of different options for that. That's not what we're here to learn. You'll be able to, but the really ham radio has always been an understanding of why this stuff works and what you can do with it. Once you know everything, you can distill it down to doing whatever you want. Using it for as little or as much as you choose. But the thing is that you have the ability to do so. All right. So now that we've covered decibels, and now you understand a little bit about, the responsibilities and stuff like that, prefixes, schematics. We're just going to flip back to schematics real quick. We did resonance, we did filters, we didn't do propagation. So we're just going to hit schematics pretty quickly. And I believe this is on page 20. Let me find this in my book. And okay, so a schematic is a layout of stuff on a piece of paper. It doesn't represent how things are actually built. It represents how things are physically connected. What wires are connected to what. Capacitors, inductors, etc., batteries, diodes. I think we've covered all that ad infinitum. An LED, it's a special diode that emits light when it's turned on in the forward direction, as opposed to just turning on. It actually spits out light. An LED is used as a visual indicator. Power gain. Oh, here's one. Which of the following can provide power gain? That would be a transistor. What unit do you think we use to measure power gain for transistors and amplifiers?
Wattage.
No. No. What is gain? Gain is ending point versus starting point. Doesn't matter what the starting point is. It's decibels. Decibels are everywhere. Decibels, you'll probably hear the word decibels 100 more times during this class. You'll learn to literally hate that word. We've got two different kinds of transistors. We have a bipolar junction transistor, which is emitter-based collector, and then a FET, which is a field effect transistor. This is just memorization. It has a gate, a drain, and a source. Okay, how things are connected together is a schematic. Just out of curiosity, everybody, this is open mic time. What's element number 4 on that drawing?
Battery.
It's battery. Open mic time, everybody. How about element 2?
Transistor.
Transistor. Specifically, that's a bipolar junction transistor. So it has three terminals, the base, the collector, and the emitter. The base is the one on the left-hand side. The collector is up top, and the emitter has the arrow on it. And specifically, this is an NPN transistor. And the way we know that it's an NPN is because it's not pointing in. That's the best thing I ever learned. Not pointing in. Well, there you go. And not pointing in, NPN.
There you go.
All right. Next one. Does everybody know what this is? We've drawn them a couple of times.
Power supply.
That's a power supply. Yeah. Okay. What's thing number 4 on this drawing?
Transformer.
Transformer.
That's a transformer. And what's the function of a transformer?
Step up or step down.
AC or DC?
This one's AC.
Actually, every transformer is AC.
Confirm. Yep.
Transformers don't do anything other than at AC. Otherwise, they're just a couple of coils.
Yeah, rectifiers from AC to DC, right?
Correct. And
There is one.
Go ahead.
There is another function of a transformer.
Well, impedance matching.
Or isolation.
Or isolation, yeah. We'll do it. We can cover impedance matching, but that's really for the general exam. So, but in the process of changing voltage and current, because impedance and resistance is a function of, E equals IR or E equals IZ. This can also function as an impedance matching device or impedance transforming device. We use them in radio a lot too. This in particular is used for power. It's usually going to be a lot bigger. Number 5. What's number 5? Okay, so the cathode is marked with which end? What is the cathode marked with?
A negative.
The minus, which is the stripy side. When you see a capacitor physically, when you see a diode physically, it will look like this. That means that it's drawn like this. That's physically what it looks like. Okay, next. How about number 8? It's a diode with lights coming out of it.
Light emitting diode.
That's a light emitting diode. It's a diode with light coming out of it. And again, number 10, that's a special diode. That's called a Zener diode. That's a voltage regulation diode.
Looks like a Z at the one end.
It does. Okay.
Voltage regulator diode.
Okay. Number 3 is just a switch. That's a single pole, single throw switch. The number of poles is the number of circuits that are run by the switch. The number of throws is the different ways it can be turned. This number 3 here is a symbol on-off switch. 1 pole, 1 throw. Excuse me. Okay. Number 5 right here, that is a rectifier. The diode uses a rectifier. To rectify means to correct or to make it work straight. To rectify a problem. The problem is AC, it rectifies it into DC. Okay, let's see. This one right here. This is actually the schematic for that little box that we took a picture that we looked at in the photo. This is an antenna matching circuit.
Couple pages down more.
Number 4 is an antenna, and the 2 capacitors with the arrows through them are variable capacitors. Number 3 is a variable inductor. Again, this is an antenna tuner. And if you take a look at this is actually known as a T-type antenna tuner. Any guess why?
It's like a T.
A T.
Looks like a letter T. Yeah. Now, there's also an L-type tuner, which basically the element number 2 is missing. Typically doesn't work as well. You can also have a pi-type tuner, PI, Any guess what the pi type tuner would look like?
The number 3.
You know, better pi. So good guess though. All right, resonance or tuned circuits. We did this. Okay. Other components, an SPDT switch. Important just to cover this. Single pole, double throw.
Yeah.
So if I were to draw this, okay, so this is a switch. It has this position, which is nothing, and this position, which is closed. There's only one circuit. It would be single pole, single throw. If there was another circuit up here that it could also close going this way, that would be a single pole, double throw. I could also draw this like this. I use this at work all the time. Two separate things. That would be a double pole because it's two separate circuits, single throw. I could do this. Now it would be a double pole, double throw. Okay. A relay is an electronically controlled switch. Electrically controlled switch, it's basically a combination of a coil and a contact. Literally a coil, it's an inductor. A meter displays an electrical quantity as a numeric value. An integrated circuit is a whole bunch of components that are inside one little block. You can buy like an entire power supply on a chip. That's called an integrated circuit. A regulator controls the voltage coming from a power supply. A fuse, we talked about what a fuse is. It prevents an overload in current. And a reason to use shielded wire. Okay, now, having discussed coils and induction and stuff like that, if I draw a piece of wire and I have a current flowing through the wire, does that go around it? Every current that flows makes what kind of field?
Electromagnetic field.
Well, not electromagnetic.
A magnetic field.
Magnetic field. Specifically a magnetic field spiraling around it. What if I put another wire here and there's a magnetic field that's dancing around that other wire? What do you think that'll make in there?
Electromagnetic.
That'll make a current.
Yeah.
What if these wires are being used for completely different purposes?
What blow happens? Something up.
Well, what ends up happening
or
is
burn something up.
Well, or what ends up happening is that if these are carrying audio, then you get crosstalk. They become coupled together. In order to prevent that, what you do is you basically provide a. Why is the current going in the other direction? I want to say I think it's Lenz's law that makes the current go in the other direction when it's I got to think about that. Great. Now I have homework to do. I think it goes in the opposite direction when it's being induced, but I don't remember for sure. But now let's say that I want to create an environment for the magnetic field to exist that doesn't allow it to get outside. So I take this and I tie this to ground. What does it mean if something's at ground? How many volts is it?
0.
That means that if there's a magnetic field, the magnetic field is going to be constrained completely inside. So how much of that magnetic field is going to get outside to affect the other wire? Nothing. So shielding cable essentially allows us to run cables next to each other without them coupling together.
I have a question.
Uh-huh.
Just like in electronics, I've taken electronics labs before, and when you're grounding a circuit, it's always like you put the a wire in the grounding hole. But like if you were building something from scratch, like what does grounding actually entail? Like I always got tripped up by that because I never really understood
Well,
what it meant.
ground is
Yeah.
just a reference point. Ground can be like if you're designing a circuit board, it can be a trace on the circuit board, which is tied to your power supply negative, which in turn could be either floating or tied to your power line negative or your power line ground. It could be tied to your chassis, which is your entire frame of the thing you're building, which could then also be tied through through the cable to the building ground. So, I mean, ground can be a local thing or it can be a really big thing. It can be global.
So,
And sorry.
I was just going to say, ground in my way of thinking about it is really just a reference.
Yes, it's a zero voltage reference.
And the only absolute reference is Earth itself.
Well, that's a good question. What happens if the Earth is traveling through space and encounters another planet, which is, quote, grounded, but they're isolated by such a big distance? The Earth is actually at 1,000,000 volts and the other planet's at 5,000,000 volts. What'll happen if they get near each other?
Good.
No, really, what'll happen?
They're going to attract each other.
Well, no, you're going to get a big spark, right?
Yeah. You have a potential difference between the two.
Discharge.
Yeah. But if we're far enough away, we don't know about it, and they don't know about it.
So really, when it comes to ground, though, and I'm in the middle of this because I'm trying to design a better antenna system.
No. That's different.
Well, I know. Well, yeah, what you're talking about is the difference between an electrical ground and an RF ground.
Yes, which we're going to cover.
Okay, I'll let you cover that.
Okay.
One of the questions I was reading last night talked about return voltage that is grounded. How does that work?
Well, I mean, basically the ground in a car, for instance, is your return path to the battery.
Right.
If you think about it, your car is an isolated system, right? It's got 4 tires that keep it at a separate voltage from the road. So here's a question. Why do you never fill up a gas can in the back of a pickup truck?
Different, you have a
Oh, Dwayne, that sounded really bad.
electrostatic field.
Yeah,
difference.
you basically gasoline is not a conductor. It can actually have an electric charge. And is the gas can grounded?
No.
No. And what happens if the gas can finds its ground through the gas pump?
Bad things.
Bad things. Yeah.
Does that apply to the plastic gas cans too?
Yes, it does. That's why because if it's sitting on the ground, the electrostatic charge that it picks up actually at least has a chance of being shunted to ground.
Plastic ones because they can produce more static electricity than the metal cans.
Yep.
All
right.
Okay, wait. I just want to clarify. Sorry.
Yeah.
I'm still a little bit stuck. I mean, I don't know how much this has. Well, I think it does have to do with, making, if you were to make your own radio, but so apart from making the ground, the physical ground, like the earth, sticking it in the ground, if you make I don't know if this is the right way to say it, but an artificial ground, what in the circuitry do you do in order to tell the circuit this is where it's grounded? I don't know.
Everything that happens above a zero reference point. Usually, if you're going to have a power supply, your power supply negative is your grounding voltage.
Okay.
And you tie everything that needs a reference to ground. Everything is measured with respect to that bus.
So let's say you have a lightning discharge.
Yeah.
Yeah, and you have a big antenna tower out there, and it's grounded. All that voltage goes to ground, right?
Hopefully.
Hopefully,
if you gave it a good path.
Right.
What if it hits the antenna?
Potentially melt the
Yeah.
antenna.
So what you end up with is you have your
Or
cable.
follow the circuit back to your radio.
Yeah.
Yeah.
Well, so what you do is you insert a grounding device, which hopefully becomes sacrificial and shunts all the power to the real ground. So, all right, let's see. Electromagnetic spectrum, radio waves in free space. Does everybody remember what frequencies are HF, high frequency?
3 to 30 megahertz.
Yep. And VHF? 30 to 300.
300.
And UHF?
300 to 3000 megahertz.
There we go. 3000 megahertz can also be written as 3 gigahertz.
3 gigs.
Yep. Okay, RF stands for radio frequency, and now we're into propagation modes. And it is, let's see, it is 10:46. We will be back in 9 minutes. Good?
Good.
Okay.
Hello. Oh.
So right over here, I've depicted a square loop of a conductor. Let's say it's a wire and it's stationary and it's sitting in a magnetic field. And I've drawn a few vectors that represent the magnetic field. And you can see at least on the surface that is defined, or this current is going to increase. The current is going to increase even more, which is going to make the flux increase even more, and which makes the current increase even more. And you would have this never, or why we direction of the current, point our thumb in the direction of the current, and we see if we do that, clockwise direction over here, that too, when you do your right hand rule right over here, your fingers would coil around that way. And so once again, when you look at the surface, it would induce a magnetic field that is.
Hey, Bruce, I think we can hear your video. I think.
It's coming loud, across loud and clear.
Oh, look at that. But you couldn't see it, right? Or could you?
It's the Solomon Khan's
yes, it
right
was
hand rule video.
Khan Academy. Yeah.
Yeah.
I was just looking at that, and it is Lenz's law, and it has to do with it. It must be in the opposite direction, because if it's not, then it would just grow infinitely long, and it would just grow infinitely.
Scott, I got a question for you.
Yeah.
Why is there no emergency hailing channel in the amateur spectrum? So you've got, Citizen B's got 9, Marine's got 16, with the large influx of amateur radio users and a fallback in emergency situations. I was just curious why there's no actual hailing channel for emergencies in the amateur world.
So try backing off from the microphone a little bit, because it was like over deviating.
I was just going to ask, what was causing that?
Yeah, Dwayne, try that again.
How about now?
That's better.
So the question is, why there's no emergency hailing channel in the amateur world, similar to that of Citizen Band or Marine?
There are.
Yeah.
Oh, okay.
Yeah, there are. I mean, we have a lot of the part of the problem is that we have a lot of different bands, but they're not necessarily emergency hailing frequencies, but like on 2 meters, there's 146.52. It's a national calling frequency. If I've got a radio on, it's always scanning that. There are frequencies that are defined as, like emergency frequencies in case of like a hurricane or something. And like a couple of frequencies will be they'll just basically be identified as, emergency monitoring frequencies for all traffic. And if you're not involved, stay off. So
okay.
Yeah, there's always like 14.300. That's a maritime, I believe, a maritime frequency, largely for sailors throughout the Pacific Ocean. So, but the thing is that, a lot of it is not official. And again, that, therein lies all the flexibility that we have. So, when there's like, I know, I'm involved in some of the emergency response stuff here in Oregon. And there's basically a big game plan that exists that in case of emergency, here's your list of frequencies. You know, this is your state government liaison frequency. This is your county government liaison frequencies. Here's your city liaison frequencies. And if you're and that's one of the reasons that if you plan to participate in things like that, to to make sure that you really work within these groups, because from just like okay, it's just like me and my family. Okay, we know that if something happens, we'll go to a certain frequency or something. But if you're part of a wider response, you have to know how the whole thing works. And that's where practice makes perfect. You know what I mean? Because otherwise, with all the frequencies we have available, people are going to have a hard time finding each other, and it's just going to be chaos. All right, everybody ready to get back to this? Everybody still conscious?
Go for it.
Okay. Propagation modes. Okay, so we covered ionization, ionizing radiation, and stuff like that. But we're going to draw a picture of the Earth again, and we're going to draw the Earth, and then we're going to start looking up at the layers of the atmosphere. We live down here in the troposphere. Nice and green, lots of oxygen. As you go higher up, your air density goes down, 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 down. So then you get up to the stratosphere, and then a couple of small things, mesosphere, etc. But then above that, starting at about 50 miles up, 30, 50 miles up, you get this thing called the ionosphere. And again, this breaks up into multiple layers, D, E, and F1, F2. The only reason I can assume why it starts at letter D is because they figured there might be an A, B, and C below it, and they didn't want to use them up. So this ends at about 600 miles up. And the F layer starts at about 250 miles up. E layer is about 100 miles. D layer starts at about 50 miles. So again, we were talking about solar radiation. The ionosphere is the layer of the atmosphere, which is all the way out into space, really, at which solar radiation in the form of ionizing radiation, which is really X-rays and ultraviolet rays, are able to come down into the atmosphere, strike atoms, which are free floating in the atmosphere. Sometimes they're in pairs, diatomic nitrogen, diatomic oxygen, etc. That make up 99% of the atmosphere. And occasionally one of those photons will strike one of these atoms with enough energy that it will take it and fling an electron out from the atom, causing it to be positively charged and the electron to be negatively charged. So then you end up with all of these things floating around. When it's direct sunlight ahead, your sun is strongest, so your density of these things builds up the highest. In the evening, at night, these tend to dissipate. Positives and negatives find each other, and what happens is that this one and this one, and let's say this one and this one will find each other, and that one find each other, so your overall density goes down. There's something called a maximum usable frequency, or MUF. Maximum usable frequency is the highest frequency at which the ionization in the upper atmosphere is able to refract a signal that goes up and comes back down. Remembering that these signals are electromagnetic, and we have electric fields up there created by all those particles. So they basically they make like a soup in a way that if it's dense enough in your frequency, is not so high that it just punches right through. It can actually be bent back down. This is called ionospheric skip. This is known as the skip zone. The reason that the skip zone exists is because the steeper the angle becomes, the harder it is for a particular frequency to bend back down. And at some point, it doesn't bend back down. It just shoots right on through. So this is known as the maximum usable frequency. And maximum usable frequency is proportional to the degree of ionization that exists up there in the upper atmosphere. So that means that during the day, your maximum usable frequency during the day is higher than the maximum usable frequency at night. And we have daytime and nighttime bands. So the daytime bands, these are usually 20 meters and up. And this is 20 meters and down in frequency. And we see this every day. This is the same, also the same reason why you can't receive AM radio signals from beyond your local range during the day, because the D layer builds up. And what happens is that this is a very absorptive layer for low frequencies. What ends up happening is that during the day, this layer becomes so dense that all the low frequency, radio frequency energy that is spit up into it just gets absorbed and dissipates. Never comes back. At night, this goes away, and those frequencies can pass right through. I'll let somebody else get this. Okay. Above a certain frequency, typically around 50 megahertz or so, the chance of this being refracted back to Earth is very, very low. So these VHF frequencies pass right on through. So the chance of ever seeing ionospheric propagation on VHF is very, very low. However, this doesn't mean it's not possible. The E layer sometimes will build up really, really heavy layers of ionization, and the 6-meter band, and occasionally even the 2-meter band, will be able to be used for skip. This is known as sporadic E because it's sporadic and it takes place in the E region. This is typically a few hundred miles. Whereas normally a skip can be on the area of 2,000 miles. So because of the geometry, typically the skip isn't nearly as long. And again, because it's sporadic, it's called sporadic E, we have, very unusual conditions that let it happen. However, if you live in Florida, it happens all the time. So enjoy that during the summer months. We also, on the 6-meter and 2-meter band, we can get into all other kinds of weird stuff. This is the level at which we get a lot of meteors. We can do something called meteor scatter, which is where you basically have, during meteor showers, you have these ionized trails. Ionized trails, that's ionization. You can bounce signals off of meteor trails. We also, if you remember, about a month and a half ago, had a nice aurora in the United States. We can also take signals, aim them at the aurora, and actually get reflected signals, which I actually did for the first time ever. It was really cool. I actually got signals that bounced off the aurora. So that's called auroral scatter or auroral reflection.
I have a question.
Yeah.
How do you know, like how far your signal has bounced from? Like, what are the mathematics for figuring that out?
Well,
is it just the time it takes to come back?
No, because
really?
I mean, how fast does it travel?
A speed of light?
Speed of light. Good luck measuring that.
Oh, yeah, but I mean, if you were to bounce it off the moon, it'd be like
a
couple minutes, right?
No, it's 3 seconds.
Oh, really?
Yeah.
I thought it was more than that. Okay.
3 second
So-
round trip.
So how else would you know if it did actually bounce off like the aurora borealis or something?
If it's an auroral signal, you can hear it.
What?
Yeah. It,
What do you like
you-
how?
the next time we take a break, I'll pull up a video.
Okay. Cool.
Okay. And the same
Should
thing
get
with
should get a Doppler effect then.
you get a crazy Doppler. Yeah. Okay, let's see another one. So now we're into line of sight and tropo. Okay, so now we're going to get down a little more toward the Earth's surface. So here's the Earth again. And now I'm also going to put some water there. So what's interesting about down toward the Earth's surface is we now live in this thing called the troposphere. And the troposphere is all this air that we live in, and it heats up, and sometimes you get temperature inversions. Normally VHF signals, UHF signals, they aim up toward the sky and they go right on through. And this is how we talk to satellites, right? VHF and UHF usually pass right through the atmosphere, but sometimes they don't. What happens is that you can have temperature inversions. And if anybody has ever seen what happens if you put a spoon in a glass of water and it looks bent, that's what happens just on a very large scale. This is called a tropoduct. So it's within the troposphere and you get temperature inversions, which cause a change in the refractive index of the air and cause signals to be ducted back and forth between the surface of the Earth and the sky.
Is this just due to temperature?
Yeah.
Mm.
Yep. Temperature and density and all kinds of stuff. And in fact, between California and Hawaii, every summer there's usually a lot of ducting over the ocean. If you get up on top of like Mauna Kea or Mount Diablo in California, and you have people who are on opposite sides of that part of the Pacific, they can actually talk up into the gigahertz range just using the duct. So another thing that happens is that the signal that you put out, if it's along the horizon, because it's a lower frequency than light, will actually curve around the Earth's surface a little bit. And this is known as the radio horizon, and it's a little bit further than visible horizon because radio waves are bigger than light waves and the Earth doesn't seem quite as curved. Let's see. Why do VHF signal strengths sometimes vary when the antenna is only moved a few feet? Okay, so is it who's in the middle of taking a physics class right now? Or will be very soon? No? Okay. Okay, so here's our radio wave. Here is a reflective object. So we're going to draw a radio wave and it bounces off this thing and they both arrive at this other location. This first wave made about 4 wavelengths. This other one, 1, 2, 3, 4, was about 4.5 wavelengths. Notice that they actually had to travel a slightly different distance to get to where they're going because this one was not a straight line. It ended up being a triangle. So what ends up happening is that at the receiver, what you have is a signal that looks like this and another one of some other amplitude that may look like this. And they get added together. What is the sum of those two things? When one is negative, the other one's positive. When one is positive, the other one's negative. They're perfectly out of phase. What happens when you try to add them together?
Cancel each other out.
They cancel each other out. This is called destructive interference. You get nothing. So now, because we're dealing with macroscopic things, we're not dealing with a Michelson interferometer in your physics lab. This is one wavelength long. Let's say we're on the 2-meter band. How long is one wavelength? I just gave you the answer.
2 meters.
2 meters.
2 meters long. So if I wanted to maybe shift one of them by a little bit, I could move across the room by about a half a wavelength, because that's how far across they are. So how far would I have to move in one direction? 3
1
feet.
meter.
3 feet. What you'll experience is that if you have a handheld radio and you're listening to somebody, that if they sound weak on a repeater, or somebody happens to be walking around a room, for instance, just moving around the room a little bit will make them get stronger and weaker, and that's due to something called multipath interference. If you're doing data communications, what you'll find is that the signals fade in and out, and you will have data loss, packet loss. If you're in a moving car, this is, you're traveling at, let's say, 30 meters per second. Well, you're going through entire waves at 2 meters, 15 times every second. And it might sound like that. It sounds like you're talking to someone through a picket fence, and that's actually known as picket fencing. And that's a really, it's a very real thing. And when you listen to it, it sounds very weird, but it's being caused by going through periods of destructive and constructive interference. You can also, if you are lucky enough, take radio waves and realize that they do certain things like bounce. And so this was an actual thing that we had happen. Here's a repeater on top of a hilltop in Eugene, or outside of Eugene. And we had our buddy Nathan, who was up around Portland, and he was using his handheld radio. And this is actually a much smaller hill, but it was still going to block the path between him and this. Between him and the repeater, the distance of about 100 miles. This is much bigger. This has a name of Mount Hood, which is a very big mountain. What he found was he could actually aim a signal using an antenna at Mount Hood and bounce it off Mount Hood all the way down to Eugene. He did not have a direct path from this other in the direct direction, but he could actually bounce it off of a mountain and get the signal back home. This could also be replaced by a building. It could be replaced by any number of different things that reflect signals. There's also something called knife edge diffraction, which is a form of a single slit experiment where you basically have a mountaintop. If it's got a sharp edge and you send a radio signal up, you'll actually have it diffracting over the edge, and some of it will actually end up coming down to the ground. And that's called knife edge diffraction. All right, here's another important one. How many people have one of something that looks like this in their kitchen? And you open the door and you put your food in and you turn it on.
Microwave.
Microwave oven. Okay, excellent. What is in a microwave oven?
Inductors.
Yeah, but what is a microwave oven fundamentally?
A microtron.
I'll give you a hint.
Yeah, it's a radar range. Radar.
Okay, what's radar?
Bouncing signals.
Radio detection and ranging. This was developed because it was determined that a high power radio transmitter would heat up water. What you have inside a microwave oven is a magnetron that makes 1 kilowatt of RF at 2.4 gigahertz. That's inside your microwave oven in your kitchen. So what is the point of picking that particular frequency and that particular power level? Well, the power level is so you can heat up the water, because energy can neither be created nor destroyed. Why did they pick that frequency?
It's microwave.
What did I just draw there?
Because it excited all the water molecules,
That's
heated them
right.
up and cooked the food.
That's right. Because the resonant frequency of water molecules is about 2.4 gigahertz. So by taking RF energy and picking the cavity size in the microwave so that you don't, so you don't have any high voltages on the sidewalls or anything, you can take all that RF energy and use it to basically vibrate the heck out of these water molecules. Vibration has another name in this case. Vibration is energy, it's heat. You're basically heating up your water. So that being said, if we are instead on the UHF or microwave frequency bands, and we are transmitting like this, here's our little tower, and we're transmitting in this direction, and there happens to be a really nice big tree here. What do you think happens in the summertime? What happens to your signal?
I would think it bounce all over.
Not only that, what happens to the energy?
Gets absorbed by the tree.
Gets absorbed by the tree leaves because they're full of water. So vegetation, and in fact, has anyone ever tried to listen to like Sirius XM or some of those satellite services in a really, really bad rain? Yep. Those signals get absorbed because they're in the microwave range. Okay. Antenna polarization. We're now into antennas. Yay. Okay, so an
Question?
antenna. Yes.
Sorry. Just like, is it dangerous at any point? Because if the microwaves, heat up over time, like what level of power is it dangerous and you really shouldn't be close to like biological things or
You
whatnot?
mean like a microwave oven or a microwave?
No,
Yeah.
like if you were transmitting in the microwave frequency.
You wouldn't want to aim it at somebody. I mean, it really comes down to RF exposure and absorption at certain levels. So, I mean, there are RF absorption calculations. All of this is non-ionizing radiation, so it's not going to cause, cancer or anything like that. But it will cause heating. So you have to be cognizant of that. And I mean, to be honest, any RF causes heating of tissue. It's just a question of how much and to what degree.
Yeah, it's interesting how they figured out that they could heat them up in the first place.
Didn't they knock a bird out of the sky or something?
No, this guy walked in front of a radar dome on a plane at an airport, and it melted a chocolate bar in his
Chocolate bar.
shirt.
That's right. Yeah, another great accident. All right, let's see. So now we're talking about antennas. Antennas can be like this. Antennas can be like this. Antennas can be shaped like this. Okay, so the simplest antenna we have is going to be a half-wave dipole. How long is a half-wave dipole?
Half the wavelength.
That's right, because it's a half a wavelength. It's actually a half a wavelength, and then 95% of that. So if we start with an antenna that's cut for 146 megahertz, for instance, we would find that the wavelength is 2.05 meters by using that formula again, 300 F and lambda. Here's our little circle. We find that it's 2.05 meters. That's one full wave. Then a half wave would be 1.02 meters. And then 95% of that would be about 0.98 meters, which is about 38 inches, 38, 39 inches. We'll say 39. So for 2 meters, that whole antenna would be 39 inches long. What's important about this is that, for the most part, we are going to have a pattern that maximizes current at the feed point because of the nature of physics. What is the current at the end of a wire? And I think I asked this yesterday. What's the current at the end of a piece of wire? Can only be one thing. Can only be zero. Therefore, since the pattern has to be in the shape of a wave, and in this case, it's a half wave because we're only choosing to make it a half wave. It has to be zero at one end, and then it has to be zero at the other end. Well, it's perfectly sized so that its highest point is right in the center. So we can actually choose then to break this wire anywhere we want. We could do it over here. We could do it over here. We could do it all the way at the end if we really wanted to. What is the formula? What is Ohm's law? Everybody? Come on, what's Ohm's law?
Resistance.
E equals IR, but in this case, we're
IR.
working with impedance. So it's E equals I
IZ.
times Z. We're going to rearrange this and say that Z is equal to E divided by I. And empirically now, so we're not doing the numbers, just empirically, where is the current, if this is our current graph, where is the current going to be at its biggest point?
The center.
The center. So at the center, this is going to be big. And empirically, we can draw this, and this is more or less what our voltage curve is going to look like. And we're going to have this being small. So what's small divided by big?
Percentage.
What's a small thing divided by a big thing?
Oh, thank you.
Small thing. So it's going to be small. Remember, I said we're working empirically here, not using numbers. So our impedance is going to be small. Well, it turns out that this is about 72 ohms, which is very close to the characteristic impedance of coaxial cable at 50. You can also get 75 ohm cable. That's a pretty good thing. But now let's say we want to feed this over somewhere else. Let's go all the way to the end. What is the current all the way at the end? Looking at that
Zero.
graph, it's almost zero, right? So that would be small, right? And the voltage would be big. So it's big divided by small. So what's something big divided by something small?
Still
Medium.
something big.
It'd still be
Big.
something big, yeah. And in fact, the feed point impedance over here might be 2,500 ohms. So could we feed this directly with our cables, which ideally have the same impedance? Have you ever seen a 2,500 ohm coaxial cable? Because I have not. So this is actually known as an end-fed half-wave antenna. They're very popular today. People love these things. The reason that people love them is because they're multi-band, and I'll show you why. What you do at this point is you say, okay, well, we have this terrible mismatch here, 2,500 ohms. We're going to feed it anyway, but up here, we're going to put a little converter box. And inside the converter box, we have a device that looks like this. What is that, everyone? But isn't the transformer used to convert AC to AC?
Changes voltage.
Yeah, it's used to convert voltage. So let's say that this is a turns ratio of 100, or let's say that it's like 40. Yeah, we don't want to go that high. Let's say that this is 10 turns to 1 turn over here. If I have 1 volt on this side, how much do I get on the other side? 10 volts.
10.
Right? If I have 1 amp on this side, how much do I get on the other side? Don't say 10 amps.
1 amp.
No. Power can neither be. Come on, go back to that. Power can neither be created nor destroyed, right? The power on one side has to be the same as the power on the other side. What's the formula for power? So if the power is the same and the voltage goes up, what does the current have to do?
Has to go down.
That would be 0.1 amps. Okay, so now what's the formula for, what's Ohm's law's other formula? E is equal to IR or IZ. Z is equal to E divided by I. So what would the Z be over here? 1. And the Z over here? Come on, somebody's give me the
1.
magic number. What's 10
1.
divided by 0.1?
1.
No, 10 divided by a tenth?
No.
1,000.
It's 100. So guess what? What did I just use the transformer to do? I used it to magically transform 100 ohms to 1 ohm or vice versa. This is the other really neat thing that transformers can do. They can transform impedances. So this 2,500 ohms on one side becomes 25 ohms on the other side. Isn't that cool? I just
Is that what's called a matching transformer?
That is a matching transformer. We use these for audio. We use these for RF. They're used everywhere. And what's cool about that is that's actually pretty close that I can actually use a 50 ohm cable and still feed it. The other cool thing that I can do with this now is if I start with an antenna that is no longer cut to the right length. Let's say that this is some random length. What does my current at both ends have to be?
0.
0. Always got to start with that. And it looks like this, for instance. What would my impedance at the middle be if my current is 0?
That would be 0.
No, it would not. What's something divided by 0? What's anything divided by 0?
Infinity.
Infinity. It would be almost impossible to feed that. But I can do this and feed it over here and use that same matching transformer box and take that 2,000 or 2,500 or 3,000 or whatever it happens to be and ignore that. And I can convert it to 25 or 30 ohms. And I can feed that with 50 ohm cable This is why end-fed half-wave antennas have become so popular. Because you can't violate the laws of physics, but you can use them to your benefit. Okay, other stuff. The polarity of an antenna is defined as the direction of movement of the electric field. This antenna is up and down. This is a vertically polarized antenna. If I were to turn this antenna horizontal, so it's parallel to the ground, this would be a horizontally polarized antenna. Because the electric field is moving back and forth. Interestingly, if I were to take a signal that had a vertical polarization and the electrical field was moving up and down, and that signal were to travel through space and encounter a horizontally polarized antenna, the goal of this antenna is to pick up electric fields that are moving horizontally, but this one it encounters is going up and down. How much of the signal will be received? What do you think?
Half.
Virtually nothing. A mismatch in polarization gets you almost no signal received at all. So that is why matching polarization is very important. So now if I were to take this antenna, which is a different antenna, we're going to take this dipole. And how long is a dipole?
Half a wave.
Half a wave, right? Why were to take this antenna and instead stand it on its end? We're going to take this antenna, turn it sideways. How long is it? Still a half wave.
Just vertically polarized.
But now it's vertically polarized. And its radiation pattern is in the shape of a donut, and it extends on that horizon, and this horizon, and this horizon, and this horizon. It basically makes a donut pattern around the antenna. Parallel to the ground, right? The signal is now parallel to the ground. Why is this important?
If you're using directionally oriented signals,
yeah,
but why is it important? Might be more sensitive.
Yeah, but how about if you're trying to talk to other people in cars? What does an antenna on a car usually look like?
Always straight up and down,
straight up and
on
down.
your windshield.
If it's straight up and down, that means it's vertically polarized. That means that its radiation pattern is not selective in any one direction. It's forward and backward and up and right and left, which basically means that this antenna, which is vertically polarized, will be able to talk to all those mobile vehicles all around the place, all around town. This is typically what we do for VHF and UHF communications. Now, there are times when you would lay an antenna horizontally. You would do that for weak signal work, Morse code, digital communications, single sideband. Those are typically better for horizontal modes, horizontally polarized modes. But for UHF and VHF, typically FM, which is frequency modulation, which is what most of us do for handheld radios and stuff like that, mobile radios in cars, this is typically what we do. And in fact, we now have this antenna, which is a half wave long, and now we're going to do a little trick. We're going to take this antenna, and we're going to instead cut it in half. But now, instead of a half wave long, how long is it?
Quarter wave.
Quarter wave. And now there is there's a wire. Uh-oh, where's the other half?
It's ground plane.
We have this other thing called the car. All right. So now we have this other thing called the car. And if I am standing over here, looking with my eyeball at this surface, which is perfectly reflective, what am I going to see? What am I going to see?
The antenna.
I'm not just going to see the antenna. I'm going to see the antenna reflected in that ground plane. And what that's going to look like is, if I didn't know there was something there, I am going to think that the rest of the antenna is actually down here. And if you want, you can actually draw this out. This is what happens. You get a reflection. It makes you think that there's something else there. Well, if I am way over here looking at the antenna and I see that there's a top and the bottom, as far as I'm concerned, is there?
Mhm.
Looks like a good antenna to me. This is called a quarter wave ground plane. A dipole has an impedance of 75 ohms. This has an impedance of about 38 ohms. It's about half, 36, 38 ohms. But what does it require? This will not work without a ground plane. So a ground plane is simply a conductive surface, and it has to be connected. Now, has anybody ever seen a magnetic mount antenna?
Mm-hmm.
Magnetic mount antennas are great because you don't have to punch a hole in your roof, right? How in the world does this thing work? Okay, now I'm going to have my cable coming in. One side goes up to the quarter wave piece. The other side comes down to here, which is connected to a plate. And this is then kept apart by a piece of vinyl or something, and is held down by a really large magnet. Okay. How are these two surfaces connected? This surface and this surface.
Induction.
What does that look like?
Induction.
Nope.
Induction.
Nope.
A capacitor?
That is a capacitor. What you have is a capacitor, because at high frequencies, a capacitor is basically a short circuit. The capacitor basically allows this upper surface and this lower surface to be connected electrically. And that is how a magnetic mount antenna functions. Really, really cool device.
So that's also probably the advantage of having a metal roofed house.
It depends.
Good.
So here's the thing. A lot of the newer pickup trucks, especially the smaller ones now, are made out of the cabs are made out of aluminum.
Yeah. So in that case, if you feel comfortable punching a hole in the roof, aluminum can be a very good conductor. Of course, you got to punch a hole in your roof.
Yeah.
I remember doing that on my first car. It was nerve-wracking to say the least, but it worked great. Okay, any questions about that before we move on?
Going back to the reflective surface, and I'm a little bit confused. If the surface is not perfectly reflected, that signal would not be propagating the same way, right?
Correct. And you notice that if it's the roof of a car, you know, compared to the ocean, which reflective surface goes further? Which one is closer to something perfect?
The car?
No.
No,
Salt
the
water.
water.
I mean, it extends for thousands of miles. So go ahead and ask that question again.
If you don't have a perfectly reflective surface, does that work?
So, I mean, when you say a perfectly reflective surface, remember, we're talking a good conductor. Sheet metal is a pretty good conductor. Not great, but it's pretty good.
Well, is it
And
about reflection or is it about conductance?
electrically conductive. I mean,
Okay.
it can be a piece of metal painted black. I mean,
Oh,
my
okay.
my favorite, actually, my favorite go-to, if I need a if I need a ground plane for a mag mount antenna, I go and get a cookie sheet, a steel cookie sheet. So let me ask this. If, let's say you have this and this radio, we're just going to pick a radio. How about, we're going to take a look at this radio right here. Okay. Everybody see that? Everyone good with that?
Yeah.
Okay. So that antenna is a quarter wave antenna at 2 meters. We already determined that a quarter wave antenna at 2 meters is about 19 inches long. Agreed? We went through some calculations. We said one wave is 2.05 meters. Half wave is 1.02. Quarter wave would be 0.51. And then 95% of that would be about 0.48 meters, which is about 19 inches. So how is it then that this antenna is 19 inches long?
Coiled wire.
It's a coil of wire. Well, a coil of wire has a little bit of what? Any coil is also what? It starts with the letter I.
An inductor.
An inductor. So you need to cancel some of that out. So you have some capacitance thrown in there. Essentially, the antenna looks like that. Well, how long do you think the metal part of it is?
Coiled up 19 inches.
19 inches. It's a quarter wave. But what happens to the radiated energy where the coil is? You get some, instead of radiating outward, it radiates like upward, and then the next coil radiates down. But what happens in there? What do those do?
Cancels each other out.
They cancel each other out, which makes this antenna very inefficient. Why would we do it though?
Portability.
Portability and not jabbing yourself in the armpit. Let's say this has a gain of -6 dB compared to a dipole, and that would actually be -8 dBi, which is compared to an isotropic radiator. Why on earth would you be okay with that?
Short range.
Yeah. Well, okay. So let's take a look at, this is where we start dealing with systems. So here's my handheld radio. This is a 1-watt transmitter. This is then connected to, this puts out a signal into space. And we already know that the antenna has a gain of -6 dB because it's a crappy antenna. We know exactly what it is. That has a loss of -6 dB. We can say how much power actually comes out, and it's like 3 dB loss and then 3 dB again, which is, it turns out to be 1/4 of the power. We get a quarter of a watt, right? But we don't even need to do that. We can also say now that going through space, the path loss is 100 dB. And actually what we're going to do is we're going to start with a unit called a milliwatt. So how many dB greater than a milliwatt is 1 watt? This would be 1,000th of a watt. And this would be 1 watt. That would be 30 decibels bigger compared to a milliwatt. So then we still lose our 6 dB, 100 dB of loss. We get to our antenna on a tower. this might have a gain of 9 dB. And let's say we have 3 dB of loss in the cable getting down to the radio in the building. And then in the building, the signal strength has to be at least minus 120 dBm, which is compared to a milliwatt. So we started with 30 dBm compared to a milliwatt. Okay, so we can go through our system now, and this is where we start to understand how all these things tie together. So we're at plus 30 dBm, minus 6, minus 100. Now that minus 100, that is 100 trillion of the signal getting to the other end. Most of it's gone, but it's still enough. Then a plus 9 and a minus 3, and we add them all up. So let's see, minus 106, minus 109, minus 100. We get minus 70 dBm. So the signal that actually gets there is minus 70 dBm, which is teeny tiny. But that receiver is capable of receiving all the way down to minus 120 dBm. We are way above that, which means that even with our lousy handheld antenna, we're still getting heard. But now what we're going to do is we're going to take ourselves, and instead of being a mile from the repeater, we're going to be 4 miles from the repeater or 10 miles from the repeater. And the path loss just went up to a negative 150. Uh-oh. We go through our calculations again. And now our signal is at minus 120 dBm. The signal has to be at least minus 120 to get heard. So what are we going to notice?
Nothing.
We are right on the edge of being heard. Now, what is the easiest thing to change? Because you can't change where you are. You're standing outside. What is the easiest, what is the greatest, quickest thing to change right here?
The antenna.
Your antenna.
Your antenna, which had 6 dB of loss. If you could replace that with an antenna that was a little better, that was only minus 3, all of a sudden you're above the threshold and people can hear you again. So this is where understanding how all these decibels and relationships between cables and antenna gain and power levels, you could also bump your power level up. That would do it too. That's why people will say, turn your power up. So that's where understanding how a system is put together really becomes an asset to you. And let's see. We did sporadic E. Let me just go over here before we go to the next section. Sporadic E, we did meteor scatter, 6 meter band. You're gonna have to study all this anyway. So tropoducting, temperature inversions, microwave frequencies. Oh, and on HF, rain and fog, precipitation cuts right through it. We did this, we did that, antennas, feed lines. Okay, so what we didn't really cover, we didn't cover the Yagi. We did the Ducky. Why should you never use why should you never bother trying to use an antenna inside a car unless you're really close to the repeater system or the other station? And that's because they won't hear you. Your car is a metal box. Most of the signal gets constrained inside the box. There's also a 5/8 wavelength antenna that works a little bit better than a quarter wave. And finally, this is called a Yagi. It has a driven element and a reflector, and these are known as directors. And they're on a single boom. What's nice about this is that this gives you a forward gain in the forward direction. and a very small amount of energy coming off the back. So the effectiveness of this antenna, we have something called antenna beam width. These are known as half power points. How many dB is half? Does everybody remember that? 3 dB. 3 dB is either 2 times or negative 3 dB is a half. So how many decibels below the big part of it do you think the half power point is? How many decibels?
3.
Yep. So our 0 dB mark is here. This is our half power point. How do you think we measure the strength of the signal going forward versus the strength of the signal going back? This is called a front to back ratio. What do you think we measure that in the units of?
dB.
Decibels. What do you think we measure the amount of gain compared to a standard radiation pattern in?
Decibels.
We measure that in decibels. We measure everything in decibels. Everything is measured in decibels. And what's nice is that feed line loss, antenna power, antenna gain, front to back ratio, power levels, they're all measured in decibels. You can make them all play together. Makes calculations a lot easier. Okay, and now we're into feed lines. And how about a 5-minute break, everybody?
Okay.
Sounds good. Okay, so what was it that I promised that I'd bring up on a video of? Oh, I remember.
It's the auroral scatter.
Yes.
Hi, Larry W. Off the back scale, the antennas north, some signals. Also, after I finished hearing CW or Morse code. Copy an N0KK, I believe. Looking him up on QRZ.com. Here's a photo of his antennas. Looks like the 6-meter antenna beam is the second one from the top there. He probably has it pointed. WA9 station.
Can everybody hear?
Loud and clear.
Yeah, I think we heard it before you started screen sharing the video.
I mean, and remember that this is what Morse code normally sounds like. Let's see.
That was annoying.
Can everybody hear this?
Yeah, we hear it.
It's just a pure tone, right? And that's what it sounded like when it was sent. This is what it sounded like when it was garbled up by the Aurora.
So there's a little sample of some auroral propagation.
I actually go ahead.
There for a second, I thought my headphones battery was getting low.
You guys hear me okay?
Yeah, we can still hear you.
You can still hear me, okay. Were you able to hear a little bit of that?
Of the
Here we
video,
go.
yes.
Here we go.
Only, go ahead.
Yeah, Kilowatt 1, Florida Pacific, Victoria, K1F, TV.
Okay, Kilowatt 1.
That's what the Aurora does to
Juliet,
voice.
nice signal 5 and 9 plus Aurora. Fox, November 25, over.
Yeah, the call again is Kilowatt 1, Florida Pacific, Victoria, Kilowatt 1, Florida Pacific, Victoria. You're 5 and 9 plus Aurora. Go ahead into Fox, November 42.
QSL, Fox, November 42, and I got your call corrected.
Yeah, that's what the Aurora does to audio, to voice. Can everybody hear that okay? Okay. All right, so we're into feed lines. And let's see, feed lines, and we're going to do SWR and then safety. And I think that will be it for today. All right, here we go. Feed lines. What is a feed line? A feed line is a something or other that exists between two things in order to transfer power to another thing. And so does anybody know offhand what some common feed lines are that you might find already? Anyone? Got them around the house.
Extension cords.
Extension cord is a type of feed line for very low frequency. Other things?
Cable TV.
Coax cable for your TV, exactly. Other ones?
Yeah,
HDMI.
coax,
Yeah. HDMI.
coax for your internet.
Coax for your internet. How about your plain old Ethernet cable? Your little 2-wire, 4-wire twisted pair Ethernet cable. That's a type of feed line. Okay,
RJ45.
RJ45 jack. Yep. So, okay, so a feed line is a something or other that is designed to carry power or information between 2 points. Now, the way this and the idea, ideally, this will consume none of your power. So now, one important characteristic of a feed line is that it has, again, a characteristic impedance. And this is a little bit weird because if we have an impedance, right? An impedance is kind of like a resistance. What does a resistor do when current goes through it?
It gets hot and reduces.
It gets hot. That's right.
Slows it down.
It burns up energy as heat. Well, characteristic impedance doesn't do that. Because what we're going to do is we're first going to start with 2 parallel wires. We're going to call this the plus and call this the minus. And we're going to say, okay, every wire also functions as an inductor. Every wire functions as an inductor. It has some inductance. Well, how about 2 wires that are parallel to each other, separated by a distance? What is that? That has a name.
Capacitor.
That's a capacitor. So 2 wires that are parallel to each other, separated by a distance, can be modeled as capacitors and inductors. And depending on how you split those values apart, depending on what the spacing is like and things like that, we can actually model sections of this so that we have, look at that. That's a letter pi. That's a letter pi also. One followed by another. This translates to the letter Z. And this is a Z. And this next section is a letter Z. And this next section is a letter Z. Those are impedances. They don't burn up any power, but they definitely have an impedance. Capacitors and the inductors make those 2 wires have a certain impedance. But again, they don't really burn up any power, except the fact that they are indeed wires, and wires also have resistance, and the resistance in the wire does burn up some energy. So now what we have is 2 wires with a Z characteristic. This could be 600 ohms. This could be 450 ohms. Could be 300 ohms. Could be 75 ohms. Could be any number of different things. So we also can draw this differently. We can take this bottom wire, which we'll call that the plus and that the minus, and we're going to take the bottom wire and we're going to stretch it into a sheet. We're going to stretch it flat. So here's our plus wire. And now we're going to take the bottom wire, and not only are we going to stretch it flat, but we're going to roll it around in a circle so that it completely encases the first wire. What is this named? What is this called?
Coaxial cable.
That is coaxial cable. And you have a conductor on the inside and a conductor on the outside. And there is a spacing between the two. And you also have, because it's a piece of metal, it has an inductance. And this has a capacitance and a capacitance. And it's just basically a flattened version of the top. So now, right here, we have a Z, and we have a Z, and these repeat on, and we have a characteristic impedance. This could be 50 ohms. It could be 75 ohms. It could be 30 ohms. It could be any number of things. What makes this significant is the fact that whatever we happen to pick, so let's say we have two pieces of wire separated by a space. These wires have a certain thickness. If we were to scale this up or scale it down so that everything were exactly the same proportionally to each other, and this were 450 ohms, this is also 450 ohms. We could also make it so these are really tiny and really close together, so long as everything's still proportional. As long as the geometry is the same, it has the exact same characteristic impedance. Just a bigger version. Why would we ever want a bigger or smaller version of the same thing? So let's say that we take 3 different cables, and we're going to draw 3 different types of three different coax cables. That's the center conductor. It's another center conductor. These are all 50 ohm cables. Why would we ever pick one over the other? Everybody, let's hear it.
Depends on the application.
Okay, let's hear it.
The bigger ones can carry more current.
This can handle tons of current, which means tons of power. Okay, let's hear some other cool things or bad things. Come on, now you're now we're thinking like RF and system engineers. Well, it can handle tons of power, but let's say you're responsible for putting this all together. And this has a diameter of 6 inches.
It's heavy and bulky.
Heavy. Yeah, okay. And super bulky. And what are you going to be attaching it to?
An antenna.
How does it get to the antenna?
A tower.
It climbs up the side of a tower. Well, how are you going to make those attachments if this thing's 6 inches across? You're going to have somebody up there with some pretty heavy duty tools putting it together. How about other stuff about this super big one?
Termination.
How about the cost? This might be $50 a foot. It could be $100 a foot. It could be $150 a foot. I mean, we're literally talking the size of a coffee can. Could it produce power? No, it can't produce power outside the legal limit, but it could carry the legal limit very easily. Let's say you wanted let's say you had a 2,000 foot tall tower. What do you think the loss of that cable would be? Very big or very low?
Very low.
Very low, even at really high frequencies. So if you were putting up a 2,000 foot tall tower, you're already making a big expenditure in the tower, right? Maybe this is worth it, right? Most people don't have the pocketbook to do that. How about the next cable down?
Would that top cable also be used for distance away from a tower?
It could be.
If your place was hooked up to where you'd lose less with that?
Yep, could be.
The top cable would also have a larger bend radius, likely, right?
Huge bend radius.
This have a hard time getting it around things.
Yeah. And how do you get it to the site? How's it delivered?
on big
It depends on
spools.
the site. If it's out in the middle of nowhere, you might have to put it on an air crane or something like
You
that.
helicopter it in. That's right.
Yeah, huge spool.
On a huge spool. Maybe it's a 12-foot spool because it doesn't bend.
It's like undersea cables.
Yeah. So, okay, but it's still 50 ohms. It's still a 50 ohm cable. How about the next one down? Let's say that this is let's say this is 1 inch across. Advantages and disadvantages.
A lot lighter weight,
A lot lighter weight.
probably lower cost,
Yep. Small dollar sign.
more flexible.
More flexible. Let's say this could handle 20 kW of power. This one's only good for 1 kW. Depends on the application. Maybe that's okay, right? I'll make it a little bit bigger dollars. So the top one, the connectors, as you were saying, the connectors might be $1,000 each. Just for the connectors.
Tools to
Tools to do it all. Yeah. The middle one, those connectors might be $50 each. Which is still pretty expensive, but it's a lot lighter. The one on top, how do you separate the shell from the inner conductor? How do you physically separate that?
Dielectric of
Be
some
on a
kind.
special machine.
Special dielectric. And on top of that, how do you keep it from getting water on the inside, considering that most of that is filled with air?
You'd probably have to use some kind of a hot glue or something.
Pressurize it. You use pressurized nitrogen. You keep it under positive pressure to make sure it doesn't leak. It's a very expensive application.
Yeah,
The middle
nitrogen
one
is inert.
Yes. The middle one, not nearly as much. If you have like let's say a 200-foot tower, you're probably getting away with that. And if you're dealing with, let's say, HF and lower VHF, you can probably get away with it. The upper one, you can be good all the way up into VHF and UHF, like a TV station. Now, why does that make a difference? Well, I'm going to switch over to this, and we're going to unfortunately kill my share, but this is super important. Notice this chart, hopefully. There we go. Everybody see that chart? Everybody see that chart okay?
Clear as a bell.
This is a super important chart. These are different coaxial cables across the top, and on the left are different frequencies of operation in megahertz. The stuff in the middle of it is the decibels of loss per 100 feet of cable that you are using. As your frequency goes up, your loss gets worse. As your cable gets smaller, your loss gets worse. As your cable gets longer, your loss gets worse. Because it's per 100 feet. The cable doesn't know what's after the next 100 feet. Just another 100 feet. They add together. So let's pick, for instance, RG213 at 7 megahertz. So what would the loss be?
0.5 dB.
Okay. So let's say you had a 600-foot run. What would your total loss be?
3 dB.
3 dB. In other words, if you put in 100 watts, how much power do you get out? 50 watts. It's pretty reasonable, really, for 600 feet of cable. Okay, but now let's take that same cable, RG213, and let's use it at 144 megahertz, which is the 2-meter band. What's the loss per 100 feet?
2.4 dB.
2.4 decibels. Well, that's closing in on 3 just for 3 decibels just for 100 feet. So now let's say you have a 600-foot long section. So you're up to 15 decibels of loss. So you're basically losing you have a tenth and then about a quarter. So of your 100 watts that goes in, you're getting about 3 watts out. Good application for that cable?
Short range.
I don't think it's a very good application. So basically, if you're trying to reduce loss, you're going to something else. A lot of people use LMR 400. If you have a repeater with a really long run, you're not even getting away with that. You're using something bigger. So deciding what cable you're going to use for a specific application is really important. And then you start getting into this. Anyone ever heard of Heliax?
Oh, it's a pretty heavy
Notice
core.
the sizes. Here's 1 5/8, and then you need special tools to deal with it. And the connectors might be $200 or $300 a piece. But if you're putting up a repeater, maybe it's worth it. You typically wouldn't do this for yourself. So the next thing up from that is called hardline. Heliax is a form of hardline. And once you get into that range, you're dealing with a lot more expense. But now we're dealing with something like this. This is called RG58. This is our next step down. This is about 60 cents a foot. Loss is pretty bad. But when would you use something like that?
Very short range.
Yeah, and it's also only about a 1/4 inch in diameter. When would you want to use something like that? So here's your radio. And here is the front seat of your car. Here's the roof of your car. And the radio has a cable that goes like this. And you slam it in the door of the car. And it goes to the mag mount on the roof. Good application for it?
Yeah.
And you can slam it in the car door. Cable is only 10 feet long. Maybe the loss is 4 dB per 100 feet. But how long is your run?
About 6 to 10 feet.
10 feet long. Your loss is 0.4 dB, which is basically nothing. So everything is specific to the application. It's important to understand. And that's another reason why we do class, because you can spend a lot of money or not spend a lot of money, and sometimes it's appropriate to spend a lot, and sometimes it's not. Sometimes it's just completely unnecessary. Okay, impedance is the opposition of AC current. Again, measured in ohms. Most coaxial cable is 50 ohms. Most radios have an impedance of 50 ohms. As the frequency goes up, the loss increases. Difference between RG58, which is tiny cable, and 213, which is bigger cable, is that 213 has less loss because it's a bigger cable. That's just memorization and getting used to the cables. Lowest loss would be air insulated hardline. Again, it's an absolute pain to work with. Source of loss in coaxial feed line, high SWR, multiple connectors, and water intrusion. Standing wave ratio is SWR. It's a measure of how well matched a load is to a transmitter. Most importantly, you see this right here, water intrusion. If you have a cable and you have a connector and it is not sealed against the environment, what will happen to it? Especially if you live in a saltwater environment, it's even worse.
Corroding.
Ocean.
Yep, you get corrosion. You get what should be a sealed environment inside the cable, which is no longer sealed. It becomes wet. Water corrodes the copper. And how good of a conductor is corroded copper?
Pretty
What
bad.
conductor?
Pretty bad, yeah. So water intrusion is really, really bad. There's another question, which is why should you always use waterproof cable and ultraviolet proof cable whenever possible? What'll happen if it's ultraviolet, if it's not ultraviolet proof and it's out in the sun?
It'll eventually start breaking down.
It'll start to crack, and then those cracks will let in
water.
Water is the ultimate destroyer of cable in most cases. Okay. One nice thing about cable is that coaxial cable is that if it's water resistant, waterproof, ultraviolet proof, you can bury it directly in the ground. A PL259 connector. This is your standard, what's known as a UHF connector. Well, it turns out that those UHF connectors are really bad for use at UHF. Notice this, PL259 connectors are called UHF, but N connectors are much better. That is very true. So if you're using 400 megahertz, for instance, what band is the 400 megahertz frequency in? That would be UHF. The N connector is the best thing for that. UHF is only actually good for HF and VHF. Isn't that weird? It's another one of those things that we got to remember, that a UHF connector, which is a PL259, is only good for HF and VHF. Standing wave ratio. We're getting into that right now. Standing wave ratio is a measure of how well connected something is to something else. So we have our load, which is the device that uses power, and our transmission line. Ideally, this is an impedance match. Let's say that's 50 ohms. Then this is 50 ohms. Then all of the energy will be transferred from the line, transmission line, to the load and never come back. That is a perfect match. It has a standing wave ratio of 1:1. This is literally a ratio of how well matched a line is to a load. The easy way to think about this is if you have let's say a piece of rope and it's attached to a doorknob, and the door is closed and the door can't move, and you whip the rope and you get a wave that forms on the rope. What happens when it hits the door?
Stop.
No, it doesn't stop.
Goes back.
It goes back. Yeah. It goes back either above, or it echoes back going below, because the energy can neither be created nor destroyed. It either shakes the door, or if the door is really, really closed and that rope is taut, it'll reflect back. If it comes back out of phase with the inline, with the initial signal, then they will cancel each other. And what if it comes back in phase? What will happen to them? It will amplify it. They will add together. What if this is a voltage? Your transistor that's making it is good up to 40 volts, and the signal that's going out is 30 volts, and the signal that's coming back is 30 volts. What will happen to your transistor?
You fry it.
You'll fry it. That's right. Okay. This is exactly what happens when you're trying to match a line to a load. If you have a poor match somewhere, you get a reflected signal and it bounces back into your transmitter and can actually damage your equipment. So most modern equipment senses this and actually lowers the output power to protect the transmitter. And that's known as fold back. And it used to be that was not the case, and people would destroy their transmitters that way.
Is that why the standard advice is to not take your antenna off when you still have the radio powered up?
I would say so. And that's also why you never switch like an antenna from one to another while you're transmitting. Because then for that moment, you'll be transmitting into a poor match. So let's say that this load instead were 25 ohms. What will happen is some of your power will go into the load and some of your power will get reflected back on the line. So the way that standing wave ratio is measured is by looking at the signal going out and the signal coming back. This is done by something known as a directional wattmeter. It actually can determine using diodes which direction the currents are flowing and do a mathematical calculation on the forward and the reflected and figure out what the ratio is between the two. That ratio is directly determined by the impedances that are in play. So SWR up to 2-to-1, that would be okay. 4-to-1, when you get to 4-to-1, this is a serious mismatch. This right here, this would be 2-to-1. If you had an impedance of, let's say, 200 ohms, simply this would be a 4-to-1 mismatch, and that would be something that you absolutely would not want to transmit into. So in order to rectify this situation, we have another device, and the inside workings of it again look like this. Everyone remember what that was called? We saw one before.
Yep.
That's an antenna tuner. Yep, and that goes close to your transmitter, and your transmitter is looking for 50 ohms. And this is now tunable. Right here is an SWR meter, which allows you to look at forward and reflected power. And by altering the values of this capacitor and this capacitor and this inductor, it allows us to match what's happening out here. So we have a mystery impedance out here. This allows us to match it so that we can get power out to our antenna, or at least not back into the transmitter. But now let's say we have a mismatch right here where the antenna is 225 ohms and the cable is 50 ohms. Even though our transmitter is now happy, what is the mismatch right here?
It's fun.
4.5 to 1. Is that a good, even though our transmitter is happy and not getting fried, do we have a good antenna system?
No.
No. And in fact, what happens is you have power going up, some of it goes out, and a lot of it comes back. It gets back to the tuner, hits a brick wall, and bounces back up and goes out. Some of it goes out, and some of it echoes back like this way, and then it goes back turned around. So what do you have in here?
Feedback loop.
You have a loop just basically bouncing back and forth. And every time that power has to go through your cable, what happens to a little bit of it?
Signal lost.
How's it lost?
Released in heat.
Released in heat, exactly. So basically what you have is your transmitter's happy, but you have a very inefficient system. The worse the cable is, actually, the better your SWR will look, because the power, it doesn't know whether it's going out as heat or out of the antenna. It can't tell the difference. So having lousy cable can actually mask a really bad mismatch. Mismatches always end up resulting in power being lost in the cable. And we're getting close to the end, and I just want to cover one more thing.
First off, how is that reflected in the sound being transmitted to another receiver?
You know, for the most part, you will never know the difference. You'll never know the difference. The only time you'll see a difference is if it's a TV signal, because that'll cause an echo, which will cause, it happens fast enough that it won't affect the audio, but it will affect the picture. Benefit of low SWR, reduced signal loss. Everything that's lost turns into heat. We did this. What should be considered when selecting an SWR meter? You need to know what frequency and power level it's going to be used at. You can also use a directional watt meter. We mentioned that. RF power meter should be installed in the feed line between the transmitter and antenna. Okay, a device used to, yeah, go ahead. A device used to measure whether or not an antenna is resonant at a desired frequency is called an antenna analyzer. Essentially, it's a wideband transmitter that can transmit super low power outside of the ham bands and give you a full picture of what's happening. Antenna tuner, dummy load. A dummy load is basically a 50 ohm non-inductive heat, basically heat creator, that when you put power into it, it represents a perfect match and spits out all the heat, all the energy as heat. So essentially, it's a completely not working antenna, but it allows you to test your system. Again, non-inductive resistor mounted on a heatsink. And it's non-inductive because if it's inductive, what would happen to the impedance every time you change the frequency? The impedance would change. Okay, so we're going to cover modulation tomorrow. And yeah, tomorrow's going to be a busy day. You guys have asked a ton of questions, which is awesome. Okay, station safety. Do I have permission to just go through station safety real quick and electrical safety? Okay, be safe. Okay, electrical current is the ultimate thing that kills people. Electrical current flowing through your tissues causes heating. Electrical current, because essentially we're electric things. All our heart muscle, and all the signaling from our brain to our body, it's all electrical. If we get current flowing through, it'll disrupt all the cells. Disrupt your heart, stop it from beating. In the United States, 3 wires are in the wall. We have 120 volts at 60 hertz. Hot is black, white is neutral, and green is always ground. That's why we have, that's why we always use 3-wire cords. Make sure that we are, if you're running high voltage, make sure that you have interlocks and make sure that you're on a common safety ground. So tomorrow we'll also cover, or maybe even today, the difference between RF ground and safety ground. A fuse is an overload device to remove power in case there's an overload. Why should you never replace a small fuse with a big one? Because it'll allow high current to flow, in which case you can burn your house down. You only put a fuse in series with the hot conductor. And again, that's the black wire. The power supply, because it has a big capacitor inside it, can actually store a significant amount of energy. I actually learned when I was a kid how to arc weld this way, quite by accident. I tried to put 2 screwdrivers and make 1 screwdriver out of it. It almost worked. It melted chrome vanadium steel. A 12-volt storage battery, again, can blow up because it generates hydrogen. You can do that by outgassing too quickly. Antenna and tower safety. Most of you don't have a tower, so we're going to go through this quick. You need to stay at least 10 feet away from any energized power line. Watch out for and stay clear of overhead electrical wires. Last year, there was a very experienced ham who was working on a tower crew, and there was an antenna as it was being lowered off a tower that got hung up in a guy line, and he went over to grab it to keep it from moving too close to something and getting tangled up. And the other side of the antenna, like a good distance away, hit a power line and he died instantly. This is somebody with years and years of experience. So we can sometimes suffer from tunnel vision and not notice the hazards around us. That's why it's always important to have a spotter to say, hey, don't do that. Don't use a utility pole because the power lines are not yours and they might be energized anyway. During transmission, you can get an RF burn, radio frequency burn, which hurts a lot. Radio frequency energy travels on the surface of conductors. It's known as the skin effect. That way, when you touch something, if it's energized and it's metal, and it's carrying RF energy, it can actually poke a hole right through your skin. Feels really bad. When climbing a tower, always use a harness. Never tie by yourself, and always tie off whenever you get to a point where you should tie off. Never ever climb by yourself. If you're going to use a crank up tower, it has to have locking mechanisms in place, or it has to be retracted. A turnbuckle is something that allows us to tension guy ropes, guy lines. They tend to loosen due to wind vibration. So we put a wire through them to keep them from rotating. If you're putting up a tower, you have to contact your local authority having jurisdiction and make sure it gets permitted using local codes. Grounding methods. If you have a tower with 3 legs, you need three 8-foot ground rods tied together and tied to the tower. You want lightning to have as easy a chance as possible of getting to ground. Putting ground wires on a tower for lightning protection. Lightning hates going around sharp bends. So you want short, direct, and gentle curves or straight lines. Bond everything together with a heavy wire or a conductive strap. And a lightning arrestor is a gas-filled tube that if your antenna happens to get hit, it will arc over to ground instead of coming into your station. RF hazards and radiation exposure. RF is non-ionizing, means it can't do cellular damage. However, it can still burn you. It can still cause heating. So you still want to be cautious. And that's what RF exposure limits are based on. The licensee, another reason that we are in class is because as a station licensee, you're responsible for the safe operation of all your equipment and antennas. You can go through and do a field strength measurement. You can do computer modeling on all your stuff, or you can just go and look up FCC OET Bulletin 65 to figure out what's safe and what's not. Fortunately, there are exposure calculators that have been turned to online websites, which make it a lot easier to do that. If you just look up RF exposure calculator, you'll find several different versions. Duty cycle, this is the percentage of time that a transmitter is transmitting. So if you're transmitting 10% of the time, that means that you can run 10 times the power as if you were running 100% of the time and still be within safety limits. Why do they vary with frequency? Because the human body absorbs more energy at some frequencies than at others. The peak is at 50 megahertz, which is a 6-meter band. And it turns out that that's about, that's 6 meters long. And a quarter wave on that, I'm not exactly sure why, but that's about 5 feet. So our absorption tends to be worst at that frequency. Ways to improve things. You can change the frequency and power level, change the distance to an antenna, and change the radiation pattern. For instance, if you have a directional antenna that's pointed that way and you're behind it, that's a lot safer than if it's pointed that way and you're standing right in it. You could relocate antennas if you need to. You can also reevaluate. Oh, you also have to reevaluate your station whenever you change any equipment. If you put in an amplifier, you change an antenna, you should really go through and do another evaluation. And I think that's going to be it for the day. Let me just, somebody was asking about this RF power calculator. And just a reminder, I'm actually going to be a little late tomorrow. I have 2 crowns getting put in at 7:30 in the morning. It should be okay, but I probably won't be home until 9 o'clock, 8:30, 9 o'clock. So I'll be here, but it might be a little late, and I'm going to send out a note to that effect as well. Here is the RF exposure calculator. Everybody see that? RF exposure calculator? Everyone see okay? Everyone still hear me? My hair's not on fire today. That's good. Our average power at the antenna. Notice that doesn't say at the transmitter. That says at the antenna. What can cause power to be dissipated before you get to the antenna?
Mismatch.
Yeah, you have a bad match, or you have lossy cable. So let's say you get 50 watts at the antenna. Notice what the antenna gain is measured in decibels compared to an isotropic radiator. Isotropic or an I is a magic antenna that doesn't exist, which puts out the same amount of power in every direction. Doesn't exist. So a dipole is 2.2. So we'll actually go with 2.2. Let's say distance to the center of the antenna is we're gonna be right on top of it. Let's go a half a meter away, and we're gonna be operating at 28 megahertz. And go. Oh, look at that. This just said, okay, power density 6.7. Legal limit is 1.1. A controlled environment is someplace that I have control over who goes in. Uncontrolled is sitting out on the street with people walking by. Well, it's a good thing that it's more than half a meter away. So I'm going to change that. I'm going to make that 5 meters. And look at that. By increasing the distance, it just became safe. So this is a really, really, really important way to understand what is safe and what's not, how to make something safe. When we put our station in at the Eugene Science Center Museum, we had to go through one of these. Every time we've made any changes to antennas or transmitters or anything like that, replace cable, you just go through it again.
Hey, Scott, could you throw in 1,000 watts and 50 feet?
Sure.
Or 45 feet. Let's do 45 feet.
On that same frequency?
Sure. Let's go to 20 meters.
Okay. A kilowatt at the antenna. Is that actually at the antenna? A dipole or something else?
It's a off-center fed
dipole. Okay. And what's your distance?
Let's call it 42 feet.
So that would be 11 meters. Yeah, 11 meters.
Okay, close enough.
And 14 megs. And
1.2.
Yep.
All right.
So
cool.
That would be fine. So and again, that assumes that you're in the pattern. So
right. Because that's how high my antenna is. And I got about 75 feet of coax. And I don't have a kilowatt yet, but eventually I will.
But that's why we go through this. And this the fact that there are websites out there for calculating this makes it a lot easier.
Yeah.
So all right. And other questions before we cut it off for the day?
Not a question.
Okay.
When in the initial email, which I think I got 27th, that I did find the zip file at the bottom of it that contains the manual and those other couple of guides, but I can't open it. Can you resend that zip file to me?
Yeah, I can also just send them as individual files. It might be that something doesn't like the zip. So
And it may be my computer or me one that doesn't work too well together.
All right. And
I appreciate it.
Just so I'm sure, it's listed as iPhone. You're listed as iPhone.
Well, my email is in. I sent you a text message originally.
Okay, so wait, what's your name, real quick?
Teresa.
Teresa. Okay.
Yeah. And do you want the email address?
No, I got it.
Oh, okay.
You're the only Teresa. So.
Yeah, I noticed that.
Yeah.
It's okay.
Okay. Anything else? I know
Good luck.
It's a lot of material. Tomorrow's going to be busy too. And again, I'll get back home as soon as I can.
Good luck at the dentist. See you tomorrow.
Thank you.
Bye-bye.
You may talk funny.
Yeah, I know.
Hey, Scott, did they already prep your teeth for the crowns?
Yes, I have the temporaries in.
I had a wisdom tooth crowned, and it took them 3 tries to get the cap to stay on.
Oh God.
They finally settled.